And so in a sense, you get this really dramatic statement that, instead of quantum mechanics being something that's difficult to reconcile with space-time, in this description of space-time, it's actually quantum mechanics that's underlying space-time, and you wouldn't have space-time without quantum entanglement in the auxiliary system. Okay. And I should mention that around that same time, Brian Swingle, who was a graduate student at MIT, had a similar idea based on a more condensed matter background, thinking about tensor networks. Okay, so that was all very quantitative. I think vague was the word Patrick used. And so obviously, we would like to be able to put some meat on those statements and tell a more quantitative story to see whether this is really true. So the first thing that we need to do in order to make progress in that direction, I need to tell you more about how to quantify entanglement. Okay, so up until now, we just talked about either the system is entangled or it's not entangled. But entanglement is something that, for which we have various quantitative measures. Okay. So let's go back to the two-spin system. Okay. And we could ask this question, what is the state of the first spin? So say someone gives me this state of the two spins, what is the state of the first spin? And I basically already told you that there's not going to be, that the answer is not going to look like this. Okay? There is no state of this form for a single spin that will give the same results for measurements as if I measured the first spin in this general state. Okay? So that's another way of saying that, that you can't, that there are definitely states that have entanglement. And so instead, what you have to consider is a more general concept. So if I have a state with a couple of spins, and I want to know what is the state of the first spin, how do I describe that? The way to describe it is through what we call an ensemble. Okay? So there's no single quantum state that will reproduce all those measurements. But it turns out that you can always reproduce the measurements by thinking about a collection of quantum states. I could take them to be orthogonal if I like. And probabilities, just classical probabilities, P1 and P2. And this ensemble of things, it'll be possible for me to choose the states and the probabilities so that that ensemble will reproduce the measurements that I would have in my original state, or reproduce, say, expectation values. Okay? And so in the ensemble, to calculate an expectation value, for example, I just take the expectation value in this state, multiply it by that probability, calculate the expectation value in that state, multiply it by that probability, and add it up. Okay, so I can always find such an ensemble that will reproduce the measurements in the full state. And so we would say that the subsystem is not described by a pure state, but rather by an ensemble. Okay. And the fact that you have these classical probabilities, we could sometimes describe that as saying that there's some classical uncertainty about the state of the first spin. Okay, so just a couple of examples that we talked about before. If I looked at these not entangled states, well, then I could say definitely that the first spin is just up with probability 1. So that's a really trivial ensemble. Same thing with this one. This first spin is in the state up plus down with probability 1. But in the entangled state, to reproduce the measurements that I would get by measuring the first spin in this system, what I would have to do is consider an ensemble where you have up with probability 1/2 and down with probability 1/2. Okay. And it's important that those two are not the same because, for example, if I computed an expectation value, there would be cross terms in using that one and not with that. Okay. So given this description of, so entangled means that I'm going to get some probabilities which are not just 1 and then 0. Entangled means I'll get a non-trivial ensemble with different probabilities. But now I can start to understand how to quantify entanglement. So if I look at this state and compare it with this one, well, naively, we would say this one is really close to the state up, up, which is not entangled. So we would say maybe that's less entangled. But these probabilities give us a way to quantify that. Okay, so this one is 99 over 100, and this is 1 over 100. And we're used to quantifying, so entanglement, having these probabilities, having classical uncertainty. This is all familiar, and it's familiar from statistical mechanics. Okay, so the other place, the first place we normally see ensembles would be when you're thinking about systems at finite temperature or systems interacting with heat baths. And then you talk about various kinds of ensembles. So you have sets of quantum states with various probabilities. This would be the microcanonical ensemble, or the canonical ensemble. You would have these Boltzmann weights as the probabilities. And in that case, we have a very well-developed way of how do you quantify the classical uncertainty that's inherent in talking about an ensemble. And that is the entropy. So this is just the ordinary, if you plug in either this one or this one, these will give you the ordinary formulas for entropy in either the microcanonical ensemble or the canonical ensemble. Okay, so this is just a general way of quantifying the classical uncertainties in ensembles. And so that is the most natural way when we come down to asking how do you quantify entanglement. Okay? Well, since entanglement is basically equivalent to having this classical uncertainty in the ensemble describing the subsystem, we could just use entropy. Okay, so here's say a general quantum system. We consider a subsystem. That subsystem will be described by some particular ensemble. I can find some orthogonal states there and probabilities there. And now, if I wanted to say, well, what is the entropy of that ensemble, I just use that same formula. Okay? And we could use that subsystem entropy as our measure. It's one possible measure, a very natural measure of how much entanglement there is in a system. Okay. So in some ways, calling it entanglement entropy, it obscures the fact that it's really just the regular entropy of the subsystem. Okay, so now we have a quantitative measure of entanglement in systems, and now the next piece of the story is that that quantitative measure is going to be precisely related to something quantitative in our description of the spacetimes that these states are supposed to describe. Okay, so entanglement entropy in CFT is quantitatively related to spacetime geometry. Okay, so this, it turns out, is actually just, it's in some sense a beautiful generalization of something that we already knew. Okay, so this statement, this connection, which is going to be, in some sense, people have described it as a Rosetta Stone for understanding the connection between quantum mechanics and gravity. If you ask, well, where was the first place that we saw it? It was actually the work of Jacob Bekenstein in 1972. And so what he observed was that in gravitational physics, there appears to be some connection between a geometrical quantity, the area of a black hole horizon, and a thermodynamic quantity, entropy. Okay, so he observed that the area in black hole geometries obeys various laws, like a first law and a second law, that are qualitatively similar to laws of thermodynamics, and suggested that this area can actually be interpreted as the entropy of a black hole. Okay. We understand that now in the context of ADS CFT. So at the time, people didn't have the tools to really understand what that entropy was counting. What kind of ensemble were you talking about? Let me explain that connection in the modern context of this ADS-CFT correspondence. Okay. So this ADS-CFT correspondence is saying that you have a description of a gravitational theory, which is just a quantum field theory. I've drawn it living on a sphere instead of a plane. So remember I said that to describe a black hole through this correspondence, you just put a whole bunch of energy into the field theory. Okay. And so our understanding now is that the fundamental description of this black hole in this space-time being described this way would just be a field theory, say, in a very high-energy thermal state. Okay. Well, now we have an understanding of what this entropy could be counting. So in the gravity picture, you've got the area of the black hole horizon. It's behaving like an entropy. And the reason is, it is the entropy in the fundamental description, in this field theory description that we're using to define our theory of quantum gravity. Okay. So the field theory is in the canonical ensemble. You have all these probabilities. You can calculate the entropy. And then the connection would be that the area of that black hole horizon is equal to the entropy of the field theory. Okay. So that was a connection seen in 1972. Now we understand it in ADS-CFT. And the statement about entanglement entropy, I think you should understand this as a massive and beautiful generalization of that statement. Okay. So what Ryu and Takeyanagi basically said was, well, instead of considering the entropy of the entire field theory when you're in a thermal state, suppose you're in just any old state of the field theory that has one of these, we're in a field theory where you have a state that has a gravity dual description. So it's a special field theory that actually is connected to gravity somehow. And we're in a state where you have a certain geometry. Maybe it has a black hole, maybe it doesn't have a black hole. And now they said, well, don't even consider the whole field theory, just consider a part of it, any old part of that field theory. And compute the entropy of that. Okay? So compute the subsystem, the ensemble describing the subsystem, compute its entropy, and they said even that thing has a geometrical interpretation as some kind of area in the dual geometry. Okay, so we went from looking at just a particular class of states, black hole states, and the entropy of the whole thing, and we said that entropy was dual to a certain area, the black hole horizon. After Ryu and Takeyanagi, we can consider any state, we can consider any subsystem of this field theory that is defining our gravity theory, and the subsystem entropy corresponds to some area in the space-time. Okay, so I'm going to tell you more about this. I think at this point I probably need to tell you more about what entropy of a region of a field theory means. You might not really have a good picture of that. And I need to tell you why they would have suggested this. And I will tell you exactly which area they were talking about. Okay, so I want to start with just what does this entanglement entropy mean in quantum field theory. We'll start with a really simple example, going back to the spins, just so you see something very specific. Remember, we were talking about states like this, where you could choose the coefficients here. And so just so you can see what it looks like, if I vary the coefficient alpha between 0 and 1, then this entropy of the subsystem, the entropy of the first spin, well, it increases from 0. It's maximum when those are equal, and it goes back down to 0. Okay, so we can easily imagine doing that calculation. We just calculate these probabilities, plug it into the formula. Okay. The next step towards field theory would be to consider, instead of 2 spins, we have 2 oscillators. Really, the only difference is you have now an infinite number of possible basis elements. But if I have 2 uncoupled oscillators, then the ground state looks like that, and there's no entanglement between them. If I have a coupling between them, okay, well, then I have to do some harder work to figure out what the ground state of that system is. It's a good third-year quantum mechanics problem. And the answer looks like this. Okay? And now, because you have this superposition, you realize that now the quantum states of the two spins are correlated. You have entanglement. And you could go ahead and, again, you could calculate the entanglement entropy between the two oscillators in the ground state of that system. Okay, so you would basically be doing a linear algebra problem of taking that set of coefficients and finding eigenvectors and eigenvalues of the matrix here. Okay. Okay, so that's what entanglement would mean for oscillators. And now you can consider a whole bunch of oscillators. Okay, so once you get to more interesting systems like that with lots of parts, there's actually lots of different entanglement entropies that you could talk about. I could talk about this particular oscillator. That one's going to be described by some ensemble of single oscillator states, and it has an entropy. Or I could consider that combination, or I could consider those three, or I could even consider some disconnected kind of combinations. So starting from the ground state of this system, I could actually ask about the entropy of any possible subsystem. So there's actually a lot of information there when I start asking about entropies in quantum systems. Okay, so field theory, well, the simplest example of a field theory would just be, it's just a continuous system. And one way to get to a field theory would just be to consider a system like all those oscillators coupled together, and then take a limit where I'm only interested in physics at very large scales compared to the oscillator distance. Okay. So there's a natural thing to look at in that kind of situation, and that would be, well, how does the entanglement entropy, or how does this subsystem entropy behave as I look at larger and larger subsystems? And so there's a nice result for this particular system of balls and springs. In the limit where this L is much larger, or the L contains many, many balls, you get an answer that looks like this. So L divided by epsilon. A technical point is that this quantity is actually, when you take a limit of epsilon going to 0 with L fixed, it actually diverges. So you have to be careful, as usual in quantum field theory, to work with quantities that are finite in the limit where you have continuous physical quantities. But you could consider things like the derivative of that quantity with respect to L, or differences between fix the subsystem and consider the difference of entropy of a given state compared to the ground state. Okay. So the field theory that set of balls and springs defines is actually a very special one, because it turns out in the continuum limit it has a scaling symmetry. One can actually prove that any quantum field theory with a similar symmetry as that simple one defined in terms of the balls and the springs, actually has an answer that also looks like that. And the only difference is that you have a different coefficient in front. Okay. So this is actually the universal answer for the entanglement entropy of a subsystem of the ground state of a conformal field theory. So the field theories with these scaling symmetries. Okay. And it was this answer that I think inspired Ryu and Takeyanagi to make the connection with gravity. Because it turns out this answer right here is also the answer to an interesting geometry problem. Okay. So it's the answer to a quantum mechanics problem. It's the answer to a geometry problem as well. So now I'll tell you the geometry problem. So the geometry problem is to consider a space. And so this is supposed to be something like a projection of a certain curvy space. So like when you project the globe onto a flat map, and distances on the map up near, well, at least there used to be distances up here, were actually shorter than they looked, and distances near the equator were longer than the ones up here. So that's what these lizards are supposed to represent. The lizards tell you the axial distance between points in this curvy space that's being represented this way. Okay, so this is the hyperbolic plane, and the distance between this point and this point would be the minimum number of lizards on, if I think about the various paths, the distance is just the minimum number of lizards that you have to go through to get from one point to the other. Okay, so the geometry problem, for which this is the answer, is just to pick any 2 points on the boundary. Okay, so actually it's an infinite distance to the boundary, so I define this little dotted line, and the distance there is epsilon. That's the epsilon that was there in our field theory problem. So the geometry problem is to find the minimum distance between this point and this point through the space. Okay. And you'll notice, well, if this were ordinary space, you would just go in a straight line from this point to this point. But in this space, you'd have to go through an awful lot of lizards to do that. And you get a shorter path, actually, by going into the middle, where the lizards are bigger. Okay. So the answer to how many lizards does it take to get from here to here for general points separated by L is log of L. It's the same answer as that field theory problem. Okay. So of course, that could be a coincidence. But it turns out to work in higher dimensions as well. So if you look at the vacuum state of a conformal field theory in higher dimensions, and you consider a ball-shaped region of that, so this is some generalization of that interval, and you ask, well, how big is the entanglement between this region and the rest? How much is the entropy of that subsystem? Well, it also has the same answer as a higher dimensional version of that geometry problem. Okay, so there's higher dimensional hyperbolic spaces that generalize what I showed you on the last transparency, and that answer matched as well. Okay. And so I think, this, and really, of course, together with the previous connections between entropy and area that appeared in gravitational physics, suggested to Ryu and Takenagi that, well, maybe in fact, we could go away from just the vacuum state, and maybe we could just consider general regions. Maybe there are certain special field theories where this connection is always true. Okay. So what I told you actually is true for absolutely any conformal field theory, the lizard answer and this one in higher dimensions. But what they were saying is that, well, maybe the special thing about these ones that are describing gravity theories would be that this always works. Okay, that you could take a general state, which might be dual not to that hyperbolic space, but to some deformed version of it, and calculate the entanglement entropy of any region, and maybe the answer is still this minimal area in the corresponding spacetime. Okay, and so if that's true, if their conjecture is true, that would give us a way of looking at a quantum state in one of these theories, doing some entropy entanglement calculations. We would quantify the entanglement of various regions. And then from that information, we could potentially deduce that there's a dual geometry that's describing things here. Okay, so the procedure would be, assuming that their conjecture is true, you take your quantum state, you calculate the entanglement entropy for lots of different regions, and then you ask, is there some kind of geometry, which is not that simple hyperbolic space, but it's some curvy, deformed version of it, where for every region A, the answer to that entanglement entropy is the minimum area surface, or the area of the minimal area surface in that corresponding geometry. Okay. And that would be a way, and if you could find it, if there is a geometry that captures all that information, they would say, well, that's the way that geometry is encoded in your quantum state in this ADS-CFT correspondence. So the summary so far would be, well, let me just tell you that this conjecture, it's a big leap, but it turns out to pass many consistency checks. And we now have a proof, or at least, I mean, some people would call it an argument, a very compelling argument by Maldacena and Lukowitz as to why this should be generally true. Okay, so it's actually been understood. Originally, it was really just a proposal. Now it's something that's on rather firm ground. Okay, and so the summary would be: so space-time and geometry is indeed encoded in the entanglement structure of the quantum state, but now we can make that statement quantitative, and I can tell you, at least in principle, how to figure out what the space-time geometry looks like if you give me the quantum state and you tell me that there's a geometry. All right, so going on from there, of course, gravity is more than just the statement that you have space-times and they can be curvy. There's some specific constraints that these space-times satisfy. Okay? They satisfy Einstein's equations. And so it's not just any geometry that's a consistent geometry in a theory of gravity. There's a very special set. And so an interesting question is, well, if geometry is related to the entanglement structure in some field theory states, can we actually learn about the constraints on geometries? Can we learn about space-time dynamics using some knowledge of constraints that entanglement has to obey? There's this entire field of quantum information theory where people have been deriving results about entanglement for years. Can we take some of those, use this magic Rosetta Stone that Ryu and Takeyanagi have given us, and see what they imply about the geometries described by these quantum states? Okay. And so as an example of some of these constraints that entanglements entropies have to obey, well, there's actually a whole list. You can open up a textbook on quantum information theory and find things like subadditivity, which says that if I have two different subsystems, then the entropy of that one plus the entropy of that one is always greater than or equal to the entropy of the combined thing. Okay. And I have fancier versions of that strong subadditivity, and there's a list of quantities and a list of inequalities. And now we could basically look at any one of those, and if someone gives me now a geometry and they say, well, hey, this geometry right here, it is encoding the entanglement structure of a quantum field theory state. Okay. Well, I can go and check. I can calculate the entanglements based on the geometry, and I can check whether these things are satisfied. And there are many geometries where those would fail to be satisfied. Okay. And so I can now learn about gravitational physics directly from these basic results of quantum mechanics. Okay. So I just have time to tell you about one example of that. And it's basically the first example that you'd think of doing. So if you start from empty space, so the vacuum state, we said that the entanglement entropies in the vacuum state of a field theory match with the areas in this hyperbolic space, or actually it's the time-dependent version of that is called anti-de Sitter space. So we already, in some sense, we've checked that anti-de Sitter space gives you entanglement entropies that seem to satisfy all the constraints. Well, now what I want to do is look at spacetimes that are close to anti-de Sitter space. So I'll just take one perturbative step away from anti-de Sitter space, consider the family of possible spacetimes, and ask, out of that family, which ones are consistent with everything that I know about entanglement? Okay. So there's one particular constraint that entanglement satisfies that turns out to be very useful here. Okay. And this is basically related, it's directly related to the first law of thermodynamics. Okay. So I'm going to tell you a version of the first law of thermodynamics that might be a little bit different than the one you're familiar with. But it's the same setup. You have a system, you have a heat bath. You start out in the thermal state with temperature T. And now consider any variation of the quantum state. Not necessarily one to a nearby equilibrium state, as you often do in thermodynamics. Consider any variation of that state to a nearby state. Well, then it turns out that the change in entanglement entropy, which is something that I can always compute. Thermodynamic entropy, we usually assume that you're going to a nearby equilibrium state. Entanglement entropy of that system is always well defined. So I ask, how does that change if I vary the state a little bit? Well, it turns out that it's always equal to 1 over T times the change in the expectation value of the Hamiltonian for that system A. So it's kind of an exact quantum version of the first law of thermodynamics. In these conformal field theories, when you're in the vacuum state, so the simple state that I want to start from, there's a sense that I won't explain in which the ensemble describing a ball-shaped subsystem is thermal. It's not thermal with respect to the regular Hamiltonian, but there's a sense in which it's thermal with respect to some other quantum operator. I won't go into the details, but the important thing is that the previous result on the previous transparency actually applies in this case when I start from the vacuum state and when I perturb away from the vacuum state. Okay. So if I use the result, what it tells me is that the change in entanglement entropy of this ball-shaped region as I perturb a little bit, it's related to the change in energy, in some kind of energy. And what it is, here's the energy density operator. This is the expectation value. And I integrate that over the ball with some particular weighting function that goes to 0 at the edge of the ball. Okay. So it's like a first law. It's relating a change in entropy to a change in energy. In these systems, actually, the energy density expectation value, it turns out that's related to the entanglement entropy of infinitesimal balls. So if you wanted, you could actually express this first law entirely in terms of entanglement entropies. What it would say is that if I vary my state from the vacuum state, and I calculate the change in entanglement entropies for all of those little balls, I can use that answer and do some integral and figure out what the change in entanglement entropy is for the big ball. They're not independent of one another. Okay. So because I can make that statement, which is just about entanglement entropies, and because Ryu and Takeyanagi have this formula that tells us how to translate entanglement entropy to something geometrical, I can translate this first law of thermodynamics to a geometrical statement about what happens to the geometry when I perturb the quantum state. Right? So I have that big empty hyperbolic space. Now I change the state of the field theory a little bit. That's going to bring me away from the big empty space. Now we'll have a few gravity waves or something. We'll have some perturbed geometry. But this first law is going to tell us that the area of the surface, of the minimal surface that ends on this ball, it'll tell us that that area must be related to the surfaces ending on all these infinitesimal balls. Okay. So roughly speaking, this first law will tell us that the area of this thing, or the geometry around that surface in this perturbed space, is not completely independent of the geometry there at the boundary, but they're related in some way. So you get some kind of non-local constraint on the space-time. And it's going to be true for some spacetimes, not true for other spacetimes. And actually, it's not just one constraint. It has to be true for any ball-shaped region that I choose. Okay, so this is one example. But I could apply that first law of thermodynamics to a little ball over here, or one over here, or one at a later time. It actually applies to little balls in other frames of reference if I go to a boosted frame. So there's actually a whole bunch of constraints. And it's a bit ugly on the surface because they're all kind of non-local about areas here and areas here. But if you do a little bit of math, it turns out that all those set of constraints that you get, if you combine them all together, they are exactly equivalent mathematically to the statement that your perturbed geometry satisfies Einstein's equations to linear order. Okay, so we're just talking about linear perturbations. And so, remarkably, starting from this Ryutaki-Naegi conjecture between entanglements and space-time geometry, and then asking, well, okay, what's the most basic, if I start from the vacuum state and then I just perturb a little bit, what kind of basic constraints do entanglement have to satisfy? And what do those tell me on the gravity side? Well, we got the basic dynamical rules that spacetimes have to obey in theories of gravity. And so, that's just the start of a program that is in progress with lots of collaborators. We've started, saying, well, what happens at second order in perturbations, or what happens in general? What about subadditivity or strong subadditivity? What do those things imply about geometries? So most of the things. So yeah, I'll just mention one result with Brian Swingle, that you can actually, in a certain sense, see that the source for that linearized equation is the matter stress energy tensor in the gravity side. And so you can really start to see the structure of gravitational physics coming out. At the nonlinear level, most of the constraints are not equalities, but inequalities. But what we seem to be learning about are things like energy conditions. People in gravity often talk about certain conditions that they consider to be reasonable for realistic matter. And now you have a chance of actually proving those directly based on a fundamental quantum description of your gravity theory. Okay. So, at the end of my time, to summarize, you've got this remarkable picture emerging where you started out thinking gravity and quantum mechanics are two things that are difficult to combine. People have used the words incompatible. But then you get in some sense, the ultimate plot twist where the two things, where gravity is just a different way to look at quantum mechanics. If you look at the right quantum systems and you reinterpret the fundamentally quantum things, then you get gravity. And so there's lots still to be done. There's lots of other interesting things, apart from entanglement. But it seems that this is a really, quantitative connection. And it's really, I think, a fundamental thing that we're learning about how gravity works. So I'll stop there.
An aeroplane in flight passes through countless particles of air in the atmosphere. These particles flow in a direction that is exactly opposite to the aeroplane's flight path direction. This is relative airflow, and it's important to remember that the relative airflow changes direction as the aeroplane's flight path changes direction. With respect to the motion of the aeroplane, these particles form straight lines of flow. Let's have a closer look at what happens to this airflow when it flows around the aerofoil of a swept-wing design aeroplane. As the angle of attack increases towards the critical angle of attack, the wingtips of a swept-wing aeroplane tend to stall first. From here, the upper surface airflow produces a wake of turbulent and slower airflow behind the wingtips. The swept wing design means that the wings are angled backwards, so the wingtips are located further aft towards the tail. The reduced lift, due to the stalled state at the wingtips, causes the centre of pressure to shift forward, towards the wing roots. Forward centre of pressure creates an unstable nose pitch-up moment. Reduced lift and more drag cause the aeroplane to sink. The separated airflow from the stalled wings immerses the tailplane in the low-energy turbulent airflow. The elevator effectiveness is reduced. Hence, the pilot is unable to recover from the stall. Common to T-tail aeroplane design, this is called a deep stall or superstall, and may cause the aeroplane to become unrecoverable.
T6NL. T6NL.
Engine.
Okay.
Around the horn. Restart.
Gear not done.
Just gonna try to get a relight going.
Okay.
You got her from the front.
All right, turn the
I'll fly the plane.
Okay. Okay, engine stop. Stop.
Okay,
Okay, you cool?
second, see the engine. Too hot. Okay, you ready to go?
T6NL. I'm ready.
Okay. And Mike and 2, we're ejected to the north. We have an engine failure. Okay, prepare to bat an aircraft. Eject, eject, eject.
Mike and 2, copy your break out to the north.
Multiple analysts say the deadly turbulence that SQ-321 encountered was likely a case of clear air turbulence. Turbulence is the irregular motion of air caused by obstructions to airflow around a plane, and this can be caused by many factors, but is most often caused by unstable weather patterns that trigger storms. And if you're thinking, wouldn't the pilot know there's a storm ahead? Well, turbulence can usually be detected on a plane's weather radar if they contain water particles. And pilots also receive pre-flight weather briefings that include information about potential turbulence. But as the name Clear Air suggests, there are no warnings when a plane is about to encounter such sudden and severe swirls of air.
Looking at the number of injuries, I believe that the flight encountered clear air turbulence. A plane of that size, Boeing 777, can be tossed about violently. If it's caused by normal turbulence, the cloud-related turbulence, the pilot could have avoided and will have avoided that. But clear air turbulence, there's no way of knowing when it's going to happen, where, and the severity or intensity of the turbulence.
According to the National Weather Service in the US, about 75% of CAT incidents happen in clear air, although they're not restricted to cloud-free air. Here's what we know about CAT. It usually happens in high altitudes of 15,000 feet above ground level. SQ-321 was cruising at 37,000 feet. CAT can happen when two masses of air meet at different velocities, pressure, or temperature, such as when a jet stream interacts with calmer air. Other sources of CAT include airflow over mountainous terrain, as well as when planes pass through the vicinity of thunderstorms, such as when passing horizontally 5,000 feet above a cumulonimbus cloud. There is currently no technology to detect the phenomenon. Let's retrace the flight of SQ-321. At 10:38 p.m. London time on Monday, May 20th, SQ-321 departed London's Heathrow Airport. There were 221 passengers and 18 crew members on board the Boeing 777-300ER jet. The London Heathrow to Singapore Changi route is routinely a 13-hour journey. About 10 hours into the flight, when the crew was serving breakfast, the plane entered an area over the Irrawaddy Basin in Myanmar, and that's when things went wrong. SQ-321 encountered unexpected extreme turbulence and began tilting upwards. Altitude data from Flight Radar 24 shows the aircraft was thrust up and down over the course of a minute. At one point, it reached about 400 feet or 120 meters above its original altitude before dramatically dropping back to cruising altitude of 37,000 feet.
To understand how gravity might arise entropically, let's think about a less out there system. We'll use the same thought experiment that Valinda uses in his entropic gravity paper. Imagine a long molecule that is free to move and fold in any direction. We place it in a box of constant temperature with one end fixed to the wall of the box. If we ignore any possible external forces acting on the molecule, we might expect it to just curl up. This is because of all the ways the molecule could move, it's far more likely to end up in a coiled configuration than remain straight. This is one way to think about entropy. The molecule will almost always take a more probable, higher entropy configuration of being curled up because there are way more configurations, or what we call microstates, in which the molecule is curled compared to it being straight. Being in one of the many random coiled states is a higher entropy configuration than the very few straight states. If we straighten the molecule, we have to exert a force and expend some energy to do so. If we let go, it'll curl up again because there's an effective force pulling it back. I should add that there's nothing magical going on here. The molecule shares its temperature with the air in the box, the atoms have randomly oriented vibrations and are being randomly smacked by air molecules, and these will pull and push the molecule towards random configurations, which are overwhelmingly the coiled ones. There's a simple relationship between the force required to pull the molecule or the entropic force that the molecule exerts on you. This is really saying that the amount of energy, the force times the distance pulled, is equal to the temperature of the system times the change in entropy after that little motion happens. Or that the force is equal to the temperature times the entropy gradient. And we call this an entropic force. It's exactly what you experience when you pull on an elastic band. In fact, any time you have the movement of matter in the service of increasing entropy, there's an entropic force. For example, if you force all the air in a room into a box and then release it, it'll rush to fill the room and generate an enormous entropic force in doing so. The proposal of Eric Valinda is that gravity is also an entropic force. At first glance, that seems odd. Gravity is a property of spacetime itself. Even empty spacetime, so what exactly is pushing or pulling in empty space? Valinda constructs his argument in the context of a holographic universe, in which at least one dimension of space is also emergent. He argues that the entropy of the stuff on the holographic boundary must increase, and that rising entropy manifests as gravity in the interior. To build up this idea, we're going to need to keep in mind dual pictures. Something is happening on the boundary, and something is happening in the bulk, and they encode the same thing, even if they sit very differently in our mental imagery. We'll flip between them as convenient, and even merge them slightly. But remember that these are two distinct ways of describing the same system. Okay, so somewhere in the bulk of a holographic universe we have a star with some mass. Let's see if we can figure out the gravitational force produced by the star without ever using any theory of gravity, just by visiting the boundary. To derive such a law, we want to know how much gravitational force is felt at different distances. So let's imagine a series of spherical surfaces around the star. If the star is massive and compact enough, then one of these surfaces would be an event horizon and we'd actually have a black hole. Then the entropy of that surface would be the Bekenstein-Hawking entropy. Basically, it would represent the amount of information of everything that previously fell through that surface. But even if this surface isn't an event horizon, we can give it an entropy. It's also the entropy of everything interior to that surface. But that makes the most sense if we zip out to the boundary. If this is a holographic universe, then the particles on this surface map to the boundary. In fact, the particles on surfaces of all sizes map to the same boundary and play out together, overlapping in that lower dimensional space. We want the entropy of this one surface with respect to someone outside that surface. That translates to how much information is hidden within that surface. Let's start with the holographic boundary from which our bulk universe emerges. Imagine that it emerges from the outside in. Now that's not really the case, but it helps us represent this visually. We're going to partially emerge our universe down to this one surface, so we can depict a special subset of the boundary as actually lying on this surface in the bulk. This is the part of the boundary that corresponds to everything below this surface. So from now on, when I say boundary, I mean the component of the holographic boundary corresponding to the region of the bulk enclosed by this surface. Okay, hold on for just a little bit of math. We know that this surface contains a mass, so we can say that it also contains energy by Einstein's E equals mc squared. That's the energy of the interior, but it also has to be the energy of the corresponding holographic boundary. We can also give that boundary a temperature, assuming the stuff on the boundary is in thermal equilibrium so that that energy is evenly spread over all possible states. And that n thing is just the number of possible states on the boundary and the total number of arrangements of particles inside the volume that would give you the particular values of energy, mass, and temperature. But that also corresponds to the amount of hidden information within the surface, its entropy. We know the maximum value for this. It's the Bekenstein-Hawking entropy, so the number of Planck-length squares over that surface. For our surface, let's just assume that the entropy and n are still proportional to the surface area, but presumably smaller than for a black hole. Okay, one more step. We want the gravitational force, so we need another particle to feel that force. Let's add a tiny mass and move it close to the surface, from the above emerged part of space. When that happens, the entropy of the boundary increases because the information from that object is lost to the external region. The boundary gains the same amount of entropy as dropping something into a black hole event horizon. This equation is just saying that the surface gains minimal entropy, equivalent roughly to a bit when the particle merges with the surface, which we define as it getting within its own quantum wavelength, in this case the Compton wavelength of the surface. But just like we saw with the coiling molecule, this tiny increase in entropy should have a corresponding entropic force. Whatever crazy interactions are happening out there on the boundary, they are statistically inclined to bring our particle closer to this surface because that motion increases entropy. If we bring everything together, the delta S over delta X from dropping a particle through the horizon, and the temperature from the overall entropy of the surface, all the H bars and the C's and the KB's cancel out, and we replace the area of the sphere with 4 times pi times its radius squared, and we see that the algebra shakes down to Newton's universal law of gravitation within some constant. And if that constant is 1, because we got our surface entropy formula right, then we have Newton's exact equation. We just derived Newtonian gravity with arguments that are entirely thermodynamic. This is basically saying that if objects in the bulk move in such a way as to maximize entropy on the boundary, then that motion means falling towards other masses in the bulk. Remember that Hawking and Bekenstein used gravitational theory and quantum mechanics to get black hole thermodynamics. But entropic gravity turns this on its head. It starts with thermodynamics and finds that gravity just falls out. But let's not get ahead of ourselves. Firstly, this is just Newtonian gravity. Can entropic gravity reproduce Einstein's general relativity? Well, in the 2010 paper, Verlinde argues that yes, it can, although the derivation is a bit much for this episode. In 2016, he also published another paper that argued that dark matter can be explained by this idea and that it's connected to dark energy, although this requires some extra assumptions.
Indeed, we can think about space and time as being sort of derived or built up from entangled quantum information. Even gravity comes about. But can we think about links with observations? So I told you about the observations in galaxies that we don't understand. And actually all the observations that are associated to dark matter in total. This is a way we have already determined that there's more gravity out there than we can observe. This is called a weak lensing, in the sense where people can measure how much gravity there is by looking at this bending of light. And they've determined that there's a lot of gravity here, but most of the matter is actually in this region. And so we have seen sort of, well, locations where gravity is there without having matter. So this is where there must be something, well, like dark matter. Dark matter also forms an important role in the structure formation in our universe. So people believe in this a lot. But now, if you look at what the universe is made of, the ordinary matter that we see is only 5% of what we observe. And dark matter, according to the current observations of particularly the cosmic microwave background, is about 25%. But most of the energy in our universe is what's called dark energy. So this is 95% we basically don't understand. And we wonder what is happening there. So this little yellow line is actually the light that comes from the microwave background, the earliest radiation we can observe. And there are photons, and that's a very tiny number. But if we ask, according to our current theory, where most of the entropy is sitting in our universe, it's not here, it's not there, it's not there, it's actually in this yellow line. People don't assign any entropy to dark energy. They call it the cosmological constant. They basically forget about all of this. And our current theory only describing this a little bit. And this is where we have, I think, made a mistake, and I'll tell you a little bit what the idea is. So the way that people observe the universe, we do it from our center. We look outwards, and we see this radiation coming from large distances, because when you look further out, actually, you go also back in time. The universe is expanding, which also makes clear that things are moving away from us. And there's a furthest distance we can look. And in a way, that gives us, just like for black holes, also a horizon. So to think about it this way, if things are a certain distance, they move away with us with a certain velocity. But if we go further out, eventually there will be a distance when it starts moving with the speed of light. And that means that the light cannot travel towards us anymore. And that's a distance we call the horizon of our cosmos. So in cosmology, we can describe this in terms of Hubble's law, which tells you indeed that the velocity goes with the distance, and the constant in front we call Hubble's constant. And so the distance where this velocity is equal to the speed of light is called the horizon distance, and that's measured in terms of this constant h. Now, why do I talk about this horizon? This horizon has very much the same properties as black hole horizons. And I told you horizons have information. So we can use here sort of an holographic idea of how much information can be put inside our universe. So if we would think about our universe as a very large computer where we store a lot of information, how much can there be in there? Well, not more than the horizon of this area, the area of the horizon. And that actually tells you exactly how much information is contained in the universe. So I'm going to actually tell you that this may affect things that are going on inside. because I actually want to explain where this difference comes from. So the idea will be that this information associated to the horizon actually will not be just sitting on the horizon, but also in the center, or actually over the entire universe. So the following observation I want to explain. I told you that galaxies rotate, but then their velocities don't go down, they stay constant. But this happens at a particular acceleration, always the same value for all sizes of galaxies. So this is an acceleration according to Newton's equations, but I can express the value where this starts happening in terms of the Hubble constant. If I multiply c, the Hubble constant with the speed of light, actually it's an acceleration, and this always happens when this, when the acceleration drops below this value, this is actually when this starts flattening. And this seems like galaxies know something about the Hubble constant. Actually, it knows something about even the dark energy in the universe. So indeed, this is the picture again. So this is where this galaxy is sitting. And this is our cosmological horizon. It had this distance, this size. And it has an area that we can calculate. It's the area of a sphere. And we can calculate the entropy. We can also calculate the temperature according to Hawking. It's also given by a Hubble constant. And I say this entropy and temperature are actually due to the positive dark energy and actually are carried by the dark energy, and they fill the entire universe. I think I need about, okay, I have 5 minutes? Okay, then that's about what I need. So this is where I write the same equations as I had for black holes, a temperature and an entropy. And it's an entropy we have not considered. Actually, it's a very low temperature. It's also a very low, but it's a very high entropy, I should say. This is a number which is called about 10 to the 120, while the amount of entropy that we have used for, say, photons is about 10 to the 90. So most of the entropy is actually sitting here. And actually, it's going to change the way I'm going to think about these galaxies. Here are some pictures of phenomena which look very similar. You probably can recognize that this is the galaxy, this is a hurricane, this is a whirlpool. The reason I show these pictures is that here we have water around it that's swirling. We see only the foam. Here we have air going around and we see only the clouds. But we know that there's something in the middle that makes this happen. Here we assume that it's just space-time and that this is rotating without anything around it, because it's empty. Maybe it's not, and that's actually sort of the analogy that I want to make here. I want to tell you another thing. I mean, we have been observing the universe for a very short amount of time. So if we put the entire age of the universe in 1 year, humans came into existence 1 minute before midnight on New Year's Eve. And the amount of time that we've been observing the universe is about a fraction of a second. But we've concluded a lot of things about what happened in that entire year. But this is not always possible. I want to do one experiment with you, if I succeed, because it's a little bit of tricky. Yeah, let me actually first do it this way. This is a bouncing ball, and I can calculate that it bounces, and it bounces every time the same height. So I know the theory of this, which is elasticity. I'm going to do this again, and it's going to do exactly the same thing, but the material is slightly different. Oh, I have to make it round. Actually, it does exactly the same thing. But if I put this here and I wait, this ball will stay round. This one will change. Actually, it's silly putty. It's actually a material made out of polymers. And if I wait long enough, it will start flowing. The only way I can know this is by waiting. If I would have measured it only by bouncing, I would have drawn conclusions. I would have developed a theory of this thing, which is identical to that one. But the physics is very different because we have to observe it for a very long time. So if our universe has properties of that, we have not been able to even test this because we have made observations for a very short amount of time. And actually, this is the analogy that's quite precise. And so the picture that I showed you in the beginning about a universe filled with information, that information is actually the information that I associate to dark energy, and it's filling the universe. I know exactly how much there is because I know the size of the horizon. I can calculate the information density. There's also an amount of information I can calculate associated to mass. Actually, this is a calculation that Bekenstein did already a long time ago, and I can compare the two, and then I can actually explain that something starts happening exactly when these rotations, the curves are changing. Actually, this is a paper I wrote last year, where indeed I made a calculation of what happens when mass is present in a universe with dark energy or without. And there's a lot of difference in the sense that the dark energy actually contains much more information, and you get sort of a back reaction, which is due to an elastic force. Actually, the mass is very similar to what happens in this material. And I can derive an equation that actually explains exactly this behavior. It behaves effectively as if there is some additional matter, but it's actually some additional force that's pushing the matter back. So this is actually what's being indicated here, is that there's actually an additional force due to the fact that the matter actually pushes away the dark energy. And that force effectively actually behaves like dark matter, and it explains these flattening rotation curves. It can be compared to data. Actually, this is measurements of this relation that I found. So what is plotted here is actually the acceleration that is observed. So the acceleration that observed is this one. And the mass that I put here on the right-hand side is the stars. So I've not put in anything of dark matter, but I can derive the acceleration here from only knowing the baryons, the stars. And then I can explain this rotation, the change of these velocities. And this is even actual data that show the same relation. It's called, it has a name, it's actually this equation. It's called the Tully-Fisher relation, or mass discrepancy acceleration relation. And there's also measurements that were done in Leiden by Margot Brouwer using, well, not strong lensing, it's where you have bending of light. She used weak lensing, is where you sort of distort background galaxies. You can figure out the gravitational potential. And she found nice agreement with the predictions of the theory that I wrote down actually are the blue lines, and they fit the data very nicely. There's unfortunately some errors still in the data, but that hopefully will be reduced. So this is where to make clear that these theoretical ideas actually connect to data, and there might be some observational confirmation, because this is still sort of after the fact. You might say, well, I knew that these things should behave like that. So the challenge will be to make a prediction that has not been verified, but then you can indeed test things in our universe. And so this is sort of the last picture I want to sort of leave you with, is that my way I view that we have sort of changed the view of our cosmos is that our normal language of matter, forces, and space-time is one that is sort of 20th century. We have sort of changed the language where we want to understand things like dark energy and dark matter. But in order to explain it, we have to indeed understand how these things emerge. And then suddenly you sort of find that there's much more information present, which is sort of present in this dark energy, and it can explain the phenomena that we associate with dark matter. So this may be a way of sort of visualizing the ideas I've been explaining. Thank you.
If we have perfect knowledge of the universe at any point, we can plug that knowledge into the equations of the laws of physics and determine the exact state of the universe at any other time, past or future. At least according to classical physics, in which the world is represented as particles and fields that obey the equations of physical law lockstep. Classical physics is what we call deterministic. But then along came quantum mechanics and messed up everything. In quantum mechanics, we represent the world not as particles and fields, but as wave functions. These are abstract mathematical objects that encode the physical state of a system. And like a good physics object, the wave function evolves deterministically, in this case under the Schrödinger equation. But the wave function alone doesn't tell us what you'd actually see if you tried to make a measurement. That action seems to introduce randomness into our deterministic theory. Take the famous double-slit experiment, for example. We send a particle, say a photon, via a pair of slits to land at a single spot on a detector. If we send photon after photon, they'll end up in a series of bands identical to the interference pattern that you'd expect by sending not a single particle, but a wave that traverses both slits. The quantum wave function behaves exactly like such a wave, and its evolution under the Schrödinger equation accurately predicts the shape of the interference pattern we see. However, it doesn't seem to predict the first and most obvious result of this experiment, that each photon lands at a single spot on the detector. That is, the quantum wave function stays wave-like when it gets to the detector, but we don't observe this wave, we only observe a localized particle striking the detector at a single location that seems to be picked randomly. This apparent randomness is a big deal. It suggests that nature is not deterministic after all, that we can't perfectly predict the future or recover the past simply by knowing the present. Now, sometimes things that look random aren't really random, they look that way because we don't have all the information. For example, flipping a coin only seems random because we're not smart enough to calculate exactly how the coin will spin before it lands. But the non-determinism of quantum mechanics is taken to be fundamental, at least by the dominant interpretation of the theory. The Copenhagen interpretation states that reality is fully described by the wave function evolving under the Schrödinger equation, and that observation or measurement collapses the wave function in a way that is truly random. Copenhagen became the default interpretation, or the story behind the math, despite some fundamental problems and despite opposition by the likes of Einstein and even Schrödinger himself. And some physicists objected enough to seek alternative interpretations of quantum mechanics, and some interpretations that might save determinism in the process. The two most famous alternatives to the Copenhagen interpretation are pilot wave theory and the many worlds interpretation. On the surface, they seem as different as you can imagine. Pilot wave theory is almost mundane, while many worlds feels almost more out there than Copenhagen. And yet, there are deep underlying connections between these two ideas that make them much more similar than you'd think, to the point that some proponents of many worlds claim that pilot wave theory is really just many worlds in a state of chronic denial. We've talked about both pilot wave theory and many worlds before, and those episodes are worth a look for more detail on the individual interpretations. Today's episode is about comparing them and perhaps seeing which is a more worthy successor to Copenhagen. Before we dig into the alternate interpretations, let's say a bit more about what's wrong with Copenhagen. For one thing, the Schrödinger equation tells us how the wave function evolves, but it doesn't directly give us the probability of getting a particular result when we make a measurement. That requires something called the Born rule, which just says that if you square the wave function, you get the probability distribution of possible measurements. But Copenhagen doesn't tell us where that squaring comes from. It's just accepted because it works. Another problem is that the collapse of the wave function has to happen across the entire wave function instantaneously. If the photon is detected at this spot on the detector, then the chance of it appearing anywhere else becomes instantly zero. This violates something called locality, and implies a sort of faster-than-light influence, which on its surface violates the core axiom of Einstein's relativity. So, do the alternatives do any better? Let's start with pilot wave theory. This was first proposed by Louis de Broglie and then fully developed by David Bohm. The idea is that the wave function behaves exactly like in standard quantum mechanics, but that it's not really the wave function that's being directly measured. Rather, the wave function acts to guide the motion of an actual particle, which we'll call a corpuscle to avoid confusion. An entire particle, like a photon, is a corpuscle riding its wave function, and we'll call the wave function the guiding wave mostly when we're referring to pilot wave theory. In the double slit experiment, the guiding wave goes through slits and interferes with itself to produce the classic interference pattern. But we don't measure the guiding wave, only the corpuscle. And the corpuscle only goes through one slit, riding the wave and being deposited on the detector at a single spot, although that location is influenced by the interference pattern. The guiding wave for consecutive particles might look exactly the same to us, but the corpuscle riding each one can take different paths. After many of them, they'll map out the shape of the guiding wave at the detector, but how does each corpuscle know which path to take if it's not random? In pilot wave theory, the answer to that is the same as the answer to why does a coin land heads versus tails. It's that there's information that we aren't aware of that defines the detailed path. Information that's not in the guiding wave alone. That makes pilot wave theory a so-called hidden variable theory. In pilot wave theory, the hidden information is in the form of the exact position of the corpuscle, and that isn't encoded in the wave function. We also need to add something called the guiding equation, which helps the corpuscle pick out a particular path. That depends on the wave function and on the position not only of the corpuscle in question, but also on every other corpuscle in the universe that this system is entangled with. And we'll come back to this point. So in the pilot wave picture, the world is made up of these corpuscles being pushed around by these guiding waves under the omniscient overview of the guiding equation. It's a bit like how the electromagnetic field can push around an electron, but with one enormous difference. When the EM field shoves an electron, the electron shoves back. For pretty much every type of particle and field interaction, there's this sort of back reaction, except for pilot waves. The guiding wave is completely unaffected by the corpuscle, and this is necessary if we want the Schrödinger equation to be strictly obeyed. The guiding wave will channel the corpuscle, and the guiding wave will interact with itself and with the guiding waves of other particles, but it completely ignores the presence or absence of the corpuscle within it. And this is going to be extremely important in a minute. So, if we know the initial positions of all the corpuscles, we could use the wave function to predict the result of any experiment. In pilot wave theory, the apparent randomness of quantum mechanics is not fundamental, but instead emerges from our lack of knowledge about the positions of all the corpuscles. So we've now solved, I guess, the non-determinacy problem of Copenhagen. We've also solved the question of what causes the collapse of the wave function. It doesn't need to collapse. In pilot wave theory, the parts of the guiding wave without a corpuscle just continue on, because remember, the corpuscle has no effect on it. Presumably, we can just ignore this empty guiding wave because we only detect the corpuscle. Let's now look at what happens at the detector when the photon wave function arrives. For both Copenhagen and pilot wave theory, the photon wave function reaches the screen and encounters electron wave functions in the detector pixels. An electron wave function in one of those pixels is excited, nudging electrons further down the circuit pathway to eventually release a photon from the computer screen indicating which pixel was excited, and so recording the arrival of the photon. But what happens to the photon wave function everywhere else on the detector? Well, we know it's possible for electrons to be in a state of simultaneously excited and not excited, what we call a superposition of states. That would also happen if, for example, we placed a single electron inside one of the slits. If the photon can be in a superposition of passing through both slits, then that electron enters a superposition of being both excited and not excited. That's true for Copenhagen and for pilot wave theory. In the latter case, the corpuscle of a photon really does pass through one slit or the other. If it passes through the slit with the electron, then the corpuscle of that electron follows the excited part of the electron wave function. If the photon corpuscle passes through the other slit, then the electron wave function is excited by an empty segment of the photon wave function, and the guiding equation then forces the electron corpuscle to remain in an unexcited part of its wave function, while the excited part of the electron wave function remains empty. Same at the detector. Electrons in all pixels enter a superposition of excited and not excited as the photon wave function reaches all points on the detector. And the part of these electron wave functions that become excited will in turn excite neighboring electron wave functions. All across the detector, this superposition should propagate through the circuitry, a cascade of interactions that leads to a record of the photon landing at that pixel, and at the same time, silence from each pixel. So, at least for a little bit, the world is in a complex superposition of each pixel being both excited and not. Of course, we only observe a signal from one pixel, so what happens to the cascades from all of the others? Well, Copenhagen would tell you that somewhere between the photon arriving at the detector and us becoming aware of the signal from the screen, all of the extraneous superpositions die off, leaving only one excited pixel. The wave function collapses. However, pilot wave theory doesn't collapse the wave function. It would say that an electron wave function in all pixels does enter a superposition of excited and not excited, but all of those excited states are empty of corpuscles except for one. Wherever the photon's corpuscle arrives, that electron corpuscle follows the excited electron wave function. The cascade of excitations from that one pixel all carry corpuscles. So we end up with this interesting situation where we have many similar cascades of excitation, but only one of them is real because it carries corpuscles. The rest are sort of phantoms, empty superpositions. In pilot wave theory, the cascade of superpositions doesn't end at the detector nor at the computer screen. Instead, we end up with a superposition of our brain in many states, each corresponding to an awareness of a photon landing in a different spot, but only one of these is real because it carries corpuscles. The rest are phantom corpuscle empty wave functions of our brains as they would have looked if the particle landed at the other locations. This is probably a good time to get to the many worlds interpretation. Fortunately, I don't have to describe how our double slit experiment looks in many worlds because I just described it. Take pilot wave theory and just subtract the corpuscles. The corpuscles served as markers of which of these diverging alternate realities was the real one, but the corpuscles themselves have no influence on the wave function, so they really are just labels. Without the corpuscle, all of the branches of the wave function are empty, all are ghosts, or perhaps none of them are. The wave function in pilot wave theory and in many worlds behaves exactly the same way, and that includes not collapsing and not being random. The main difference between the two is the existence or not of the corpuscles. In pilot wave theory, corpuscles mark real physical reality, while many worlds accepts that the wave function itself is the primary and really the sole elementary constituent of physical reality. Another difference is the guiding equation in pilot wave theory. Many worlds doesn't need it because the evolution of the wave function alone only needs the Schrödinger equation. This guiding equation presents its own issues. The main one is that it needs to know about not just the corpuscle in question, but also every other corpuscle connected to it via entanglement. It needs this to ensure that all the corpuscles are always funneled into the one real world. This means that the guiding equation is explicitly non-local, causing instantaneous interactions between corpuscles across arbitrarily large regions of space. In fact, we now know that it's impossible for any hidden variable theory, like pilot wave theory, to preserve locality. Because of this, no one has managed to make pilot wave theory play nice with special relativity. However, it's easy enough to make the theory relativistic if we just delete our corpuscles. But then, of course, we have many worlds. Occam's razor tells us that the simplest explanation is usually the most correct. Don't add parameters to your model if they aren't needed. Some have said that the branching timelines of many worlds is an addition that goes against Occam's razor, but proponents of many worlds say that these timelines are a core prediction of raw quantum mechanics. To get rid of them, you have to add something, either the collapse of the wave function in Copenhagen or the tagging of the one true world with corpuscles in pilot wave theory. Let's ask one more question. Do any of these interpretations explain the Born rule? We know that Copenhagen just takes it on faith that you need to square the wave function to get the probabilities, but do they fall out more naturally in pilot wave theory or many worlds? Well, in pilot wave theory, the probability of getting the measurement in a particular location depends on the distribution of corpuscles. It turns out that if you start the universe with the corpuscles distributed according to the Born rule, so their density being proportional to the square of the wave function, then at all later times they'll retain that distribution. And so the Born rule will continue to work. But pilot-wave theory doesn't tell us how the corpuscles got distributed that way in the first place. In many worlds, the probability of recording a particular measurement value is the probability of you finding yourself in a timeline where that value actually happened. So it's about the density of timelines, how many alternate realities correspond to your measurement. And the fact is, you can recover the Born rule with this sort of statistics of alternate worlds. You can calculate the probability of landing in one particular world.
And so I'll just remind you then, the key step of not starting from physics and trying to sort of squeeze consciousness out of it, not phenomenology out of physics, which is the usual starting point, at least since Galileo, but starting from phenomenology itself, which is the source of all explanation and the target in the end of all explanation. And from this, see how far we can go with an operational, that is, physical approach. And here's a key slide that basically says, okay, you start on the left, basically with Descartes. You take experience, what it is like to be, as primary. That is what exists immediately and indubitably. And then from there, you posit that there is a world outside of you, independent of you, which is physical, takes and makes a difference, and atomic. Here is indicated as a physical substance, say the brain. Within the brain, some smaller units, say neurons, or you could take anything you want. Here we have just 4 units. And we can observe them, by calcium imaging, electrodes, you name it, and manipulate it, say optogenetically. Out of this, we can basically describe, ideally, a transition probability matrix for the units. We can see the cause-effect power of this substrate at whatever level we want. And then we want to explain the properties of experience. As I said, the first important step to go beyond Descartes is to say not just that experience exists immediately and indubitably, but to ask, are there some properties which are also immediate and indubitable, but are also true of every conceivable experience? And it identifies 5 such properties and none other than those. And I'll be very, very short. Intrinsicality means that the experience is subjective. It is for the experiencer, not for somebody else, so to speak. Composition means that the experience is structured. It has what IT calls phenomenal distinctions and relations, like a left and the right side. If you imagine waking up from a dreamless nap and seeing your body on your bed in your bedroom with a book in your hands, which is blue, there is a lot of structure there. In fact, immense amount of structure, which is typically not recognized. And all of that structures the experience to be, information now, specific, the particular way it is. Every experience is specific. There is no experience that's generic. It doesn't make sense for an experience to be generic. The fourth property is integration. Every experience is unitary. You cannot decompose it into independent parts. Let's say the left side experience independently of the right side. It's always one experience. This is a property that was recognized by Descartes himself, as well as, of course, by Kant and others. And finally, exclusion. That is the property by which experience is definite in the Latin sense of having a border, a limit. So what my experience contains when I say, come out of this dreamless nap and see my bed, my body, my book, and so on, is what it contains, not less and not more. It doesn't just contain the left side or the right side or the upper quarter. It contains everything it contains and nothing more. It doesn't extend, for instance, behind my back. So every experience not only exists, but it exists for the subject in a structured, specific, unitary, and definite way. Now, the next step that IIT takes, as I mentioned before, is to translate these essential phenomenal properties of experience into essential physical properties, where I remind you, physical means operational, means cause-effect power, with then the prediction that the substrate of consciousness in physical terms should be something that satisfies those properties. Now, the translation takes quite some time to go through, and I will not. Okay, this is explored in several papers, and we are still working on sort of an optimal translation. But basically, if existence in physical terms means cause-effect power, taking and making a difference, intrinsicality means that a substrate, a bunch of units you can observe and manipulate, must be able, and I show this here on the left, to make a difference to itself. Okay, and this is the transition probability matrix of a little subset of 4 units, A, B, C, D. They must be able to make a difference, measured here in terms of the probabilities of entering one state from a different state for all possible initial states. Composition means the experience is structured, and therefore, in physical terms, its substrate must also be structured. So we don't consider just A, B, C, D, we consider a subset of it, A, B, C, A, B, B, C, B, C, D, and we get what is called an overall structure of distinctions here in brown and relations. Distinctions are mechanisms with a cause and an effect. It could be mechanism A with a cause within the system and effect within the system. It could be A, B. These are higher order mechanisms. And relations are causal overlaps between causes and effects. So you begin to get a structure. Information means that the structure is specific, just like experience is. You can't just have a generic distinction, a generic relation. It must be between specific cause state, indicated here, ABC, for instance, a cause state, where the uppercase means on, for instance, and the lowercase means off. And relations might be specific. Some causes must overlap, and if they overlap, they might be congruent. They must specify, for instance, the same cause. Integration means that you take this substrate, you unfold its structure, and then you ask, does it hang together? Is it unitary, like consciousness, or can it be separated into independent components? By this, you do a cut, indicated here by the scissors. You cut out, for instance, unit C. This is a physical manipulation. And you ask, does this make a difference to this structure? If it doesn't, it's not one structure, but 2 at least. So it's not integrated. If it does, it means that the structure cannot be subdivided physically into independent components. And the quantity phi is indeed a quantifier of how irreducible that structure is, how much the structure exists as one entity as opposed to as separate entities. Finally, exclusion. Consciousness is definite. It has borders. It contains what it contains, not less and not more at a particular grain. And here the idea is that you could consider any substrate, A, B, C, D, or you could consider a smaller substrate, like for instance, just these 3 units, B, C, D, and A is called the background condition, or a larger substrate. In principle, you can unfold in full the causal powers of any substrate, but IIT says that just like consciousness, its physical correspondent must be definite. It must contain what it contains, not less and not more. And the way we go about that is by appealing to the key principle in IIT, the maximum existence principle, that says that what exists is what exists the most. So you find the particular substrate that is maximally irreducible. This is called a cause-effect structure. In this case, the one that wins is these 4 units, not 3, not 5, and so on. And you also find, I won't go into that, the particular grain of the units, be there neurons or microcolumns or mini columns, the particular time update, be that milliseconds or microseconds, and the particular set of states that maximize existence, maximize phi. So that's the very quick translation. I just want to point out that finally, recently, this was always an important and delicate issue in IIT. We've been able to demonstrate that there is one way of measuring phi, in other words, intrinsic information and then irreducible intrinsic information, which is unique. In other words, it satisfies the postulate of IIT. It's directly derived from the postulate that I just mentioned. And it can be proven mathematically that that is the only measure of making a difference, if you wish, that does so, which is critical if you think about it, because obviously consciousness is what it is. It doesn't depend on how you measure it. And so must be the way we actually evaluate irreducibility in IIT. All of this leads to the fundamental identity of IIT, which I want to point out is an explanatory identity. From consciousness, we try to account for it in operational physical terms. And the identity says that an experience with all its specific integrated structure is identical in physical terms to a cause-effect structure, what I just showed you before, which is composed of distinctions and relations. The quality of the experience, the way the experience feels, should be accounted for completely by the distinction and relation that compose the structure, by its form, if you wish. And the amount of consciousness, the quantity of experience, is measured by phi, the measure of irreducibility, which is really a quantifier of existence. And there must be a one-to-one correspondence then between the properties of experiences and those of the corresponding cause-effect structures. So now let me just summarize all of this by saying that a cause-effect structure fully unfolds the causal powers of a physical substrate and a state. Think a bunch of neurons, some on and some off somewhere in the brain, based on that operationalization, which is the transition polarity matrix. And it does so at the optimal unit grain that maximizes existence, phi. It accounts then for the essential properties that are true of every experience: intrinsicality, composition, information, integration, and exclusion. And if the theory is right, it should account also for the specific properties of specific experiences with no further ingredients added. That is, for how space feels, time flows, and so on and so forth. In fact, this is very much the research program that is going on in the lab. It's been going on for a while. It's not an easy one, I can assure you. But the idea is to try to account from first principles for why space feels extended, time flowing, object as binding the general with the particular, and why colors and sounds and potentially in the end everything else feels that way. I will just mention, to give you a sense, how we can go about trying to explain the quality of experience. And we did that by starting from the experience of spatial extendedness, because it is pervasive. Almost all of our experiences are somehow painted, if you wish, in space, the canvas of visual space. But for that matter, the body also feels extended. Not all, otherwise it would be an axiom, but almost all are spatially extended. This is typically ignored. We take it for granted, okay? And that spatial extendedness, unlike other aspects of experience like a color or nausea or anything like that, is penetrable by introspection. We can, to some extent, understand the structure of spatial experience through introspection, which very much boils down to spatial attention in this case. The idea then is that we need to find a correspondence between phenomenology and the cause-effect structure specified by a particular substrate. We conjecture the right substrate is a grid. Here you see a 2D or a 1D grid of, say, neurons connected by lateral connection, not only. And then we unfold that cause-effect structure, and we should be able to account for the property of spatial extendedness. No further ingredients added, just the postulates of IIT. And so the phenomenological analysis, which for space is doable to some extent to introspection, identifies as basic distinctions for spatial experience, spots, for lack of a better word, which are, any subset of the canvas of visual space, for instance, or body space that you can sort of focus on. And there are, of course, a huge number of spots of any size, any location in the visual field, for instance. And then 4 fundamental kinds of relations among spots. Reflexivity, every spot points to itself. Connection, every spot can have some other spot partially overlapping with it. That's a relation. Fusion, that 2 connected spot, well, you can always find some spot which is the fusion of the 2. And finally, that for any spot, you can always find a spot that includes it or is included by it. These are really fundamental properties of spatial experience. I'll be happy to discuss that at some other level. But the key point here that I want to get across is then we take our conjectural physical substrate, a grid. Here is a 1D grid for simplicity. We unfold its cause-effect powers using just the postulates of IIT. We find irreducible distinctions, which would correspond to the spots, a particular mechanism, say DE, 2 neurons, both off, that specify a cause and an effect that are irreducible, and relations among them. For instance, reflexivity means that a cause and an effect must fully overlap. Connection means that 2 distinctions partially overlap. So their cause and their effect are partially overlapping, which gives rise to a physical relation that can be measured also in terms of its phi value, its existence. Fusion, that you can take distinctions and you'll always find one that actually is the fusion of the 2 and vice versa. And inclusion, for every distinction, you can always find another one that either is included by it or includes it. So you do this systematically. Here you just see the few ones illustrated here, and you unfold this large cause-effect structure. And you can account in physical terms as substructures for the properties of spatial experience, including all those properties that follow from these 4. These 4, reflexivity, connection, fusion, inclusion, we call extendedness. That's what really makes space feel extended. But then there are derived properties, like you experience a region, and that regional space is at a location in space. This has a direct translation in terms of what is called the subtext and the supertext of a distinction, but it all follows from unfolding the cause-effect structure. The size of a spot, the boundary of a spot, or the distance between spots. Distances are available to us. We don't need to compute anything. They're all there among any spot in the visual field. All of that exists, so to speak, physically within the cause-effect structure. So obviously, I cannot hope to go through this properly. It's a long and dense paper, but I recommend that because you will find these things properly described and the correspondence properly pointed out. So with that, I want to then briefly go to the fact that as a scientific theory, IIT is actually testable. It has explanatory, predictive, and inferential power. To me, the explanatory power actually comes first. For something as fundamental as consciousness, you need to first try to account for many diverse and basic observations with a coherent theory. For instance, you need to account for why the cerebral cortex, or at least parts of it, is critical for consciousness. Other parts of the brain that are equally or more complicated, depending how you count it. For instance, the cerebellum has 5 times more neurons than the cerebral cortex. Why are those irrelevant for consciousness? You take out the cerebellum surgically, and consciousness basically does not change. Okay. Why are some parts of the cerebral cortex more important than others, as we will see? Why not cortical subcortical loops that are key for instance, allowing me to speak now and express what I want to express? But most of what's going on there, I have no idea. Why do those not contribute to consciousness? Why does consciousness vanish early in non-REM sleep, even though the neurons, as indicated here, continue firing at roughly the same rate as they do during wake? Or why does consciousness vanish during some seizures in which neurons fire more and more synchronously than during wake? You need to account for all these facts with a coherent theory. And I'll give you only a sketch here of the idea that purely based on the postulates of IIT, you can sort of already infer that a substrate like parts of the posterior cerebral cortex, where neurons are connected in a grid-like manner and then pyramids of grids stacked upon grids, is a very good substrate that when unfolded can actually specify a giant cause-effect structure, that is high levels of consciousness, if you wish, of a certain kind. This is just an indication of the grid-like architecture of primary visual cortex, but that's true also in secondary and tertiary visual cortex. And here we see instead that for the cerebellum, despite its massive number of neurons, the fundamental organization of the cortex and the granule cells, Purkinje and granule cells, is according to microzones, which are very much like parallel sheets, very modular, which interact minimally with each other. And that's a terrible architecture for having high phi. If you unfold something like this, you get many, many little mini entities indicated here, millions of them, rather than one big entity. Okay, so that explains why some anatomies are good and some anatomies are bad, at least in the brain, which is the only place where you can test a theory of consciousness. Now, on top of that, I told you that early in non-REM sleep, you lose consciousness. In fact, a third of the time or so early in non-REM, you are unconscious as much as we can tell. If I wake you up, you say there was nothing. The anatomy is still the same. So what changes? Where we know a lot about it, neuromodulators change, and what they do ultimately is probably by, making Martinotti cell burst. That's what we suspect based on various experiments with it. But whatever it is, the end result is that the causal interactions within posterior cortex are impaired. There are so-called off periods that break down the cause-effect power. So when you're awake, the posterior cortex can specify a giant cause-effect structure. When the same person falls into deep sleep early in the night, it's almost like the cerebellum. The causal interactions among neurons in posterior cortex break down also elsewhere. And then instead of one big entity, you fragment, you disintegrate, you decompose into many little things. That's sort of the explanation. And that explanation fits with evidence. This is intracranial recordings, intracranial stimulation, intracranial recording, which basically just look here. This is awake and conscious. This is in non-REM sleep early in the night and unconscious. And the response to the stimulus is strong, but in non-REM sleep, there is a period of reduction of the high frequencies here, which basically means that the neurons stop firing, then they come back, but it breaks down, this is the phase locking factor, it breaks down the ability of causes and effects to go across 200 milliseconds or so. So the presence and absence of consciousness in very basic cases can be accounted for in a coherent way by the principles of IIT, and hopefully also the quality of experience where we can study it. I showed you the first attempt, which has been that of accounting for why space feels the way it does, that the way it feels extended is a particular kind of cause-effect structure in the context of a much larger cause-effect structure of the experience. And we conjectured it's specified by grids. Grids do that, account for space, and only grids do that. I will not really explain this slide except for saying a grid-like substrate unfolded satisfy here in gold the properties of extendedness, those four properties of reflexivity, connection, fusion, and inclusion. And similar substrate in terms of number of neurons and connections, but arranged at random. Once you unfold it, you get distinctions, you get relations of some sort, but absolutely no extendedness. So you need a particular kind of substrate, a grid, to unfold into a cause-effect structure that accounts for the phenomenal extendedness. And of course, roughly 38% we calculate of our cerebral cortex is organized in a grid-like manner. It's mostly posterior cortex is organized like that from V1 all the way up. And that is exactly what is needed for supporting an experience which is overwhelmingly spatial, like ours. There are experiments too, and there will be more, I hope, in the future, that indicate that these grids are important not just to process information as people talk, or they are important to see things. Here is an example of a lady that was studied by Marta Farah, in which before the surgery, she was asked to imagine how big a horse was, and in particular, when the horse would overflow her visual field, how close did it have to be? And she basically said 15 feet. It wasn't done just with the horse, it was done with all kinds of things. So that's how large her imagined visual field was, her spatial canvas. They took out one occipital lobe, and of course she became blind on that side, on that hemifield. That is no surprise. But also, importantly, when she tried to imagine after the surgery, for her space was basically half of what it was before. The other half did not exist. There is a full agnosia for space, and the horse would overflow her visual field when it was about 35 feet across. Okay, so this is just an indication that the lateral connections in our posterior cortical areas, according to IT, they're not just important for modulatory inference, some kind of fancy processing. They are actually there because they are what makes space exist for us. Okay, this is an experiment, as a initial experiment. Hopefully there will be more of this ilk that we did in order to test a rather counterintuitive prediction of IIT, which is that changes in connectivity without ideally changes in activity should change the way experience feels, in this case, spatial experience. So if you strengthen the connections in this little grid, once you unfold it, you get a cause effect structure that will correspond to a more contracted experience of space. And so we used some tricks. We basically used very rapid flashing of two bright dots at a particular location in the visual field during training. And before and after training, we checked how psychophysically, how far apart two dots presented, for instance, here were from each other compared to other two dots. And so we could do that pre and post-training testing. The training is supposed to produce a strengthening of connections indicated here between the corresponding topographically mapped regions in visual cortex, presumably mostly primary visual cortex. And indeed, we observed that for subjects, the two spots presented after training, where the connection was stronger, looked closer. The most important test is down here. If you stimulate now in two far away regions of the visual field, where you produce no potentiation, no flash, rapid flash, and so on and so forth. So presumably you didn't change the activity patterns that you elicit here when you present these two spots before and after training. All you changed was the strength of the connectivity here in the middle. Even so, as predicted by the theory, space would contract. So this is the kind of experiments, for instance, which are counterintuitive. You change connection strength, you don't change activity patterns to the extent you can actually have that, and the experience will feel different. So I will finish with the predictive power of IT, at least some examples of the predictive power, not just explanatory power, but predictive power. Most of the work that we did from the start was to look at big stuff. When you're conscious versus when you're not, when consciousness is present or not. Will some poor man's proxy of phi, of integrated information, indeed behave as predicted? High when you're conscious, low when you're not. So we developed an approach with TMS-EEG in which we would measure the complexity of the response across the brain with 60 channels of EEG. This was done with Marcello Massimini, who has been continuing this line of work. You can see here a complex response in the EEG, and here is sort of a compressed version over time. You see many brain regions, cortical regions being involved at different times, typically up to 400 or 500 milliseconds. The same subject, when unconscious early in the night, the response is much simpler, as you can see here. And in practice, what happens is there is a strong response, but it's only local. It stays there where you stimulate, and it doesn't really propagate anywhere else. It dies off very quickly. Okay, so that was according to the prediction of the theory. And then from then on, more difficult experiment, we tried to see whether when you started dreaming, for instance, in REM sleep, the response should go back to be similar, indicating high integrated information to when you're awake. And indeed, it did, unlike an unconscious state of sleep. And then anesthesia. Here you see midazolam anesthesia. That was the first set of experiment we did in Madison, and propofol, xenon, and notice ketamine. So these three anesthetics, where the subject is not there, is really gone, led to a response which is not complex as predicted by the theory. The critical one was ketamine, because it's an anesthetic which is not really used in adults now, but it was initially. It produces complete unresponsiveness. You can do surgery, but subjects dream very intensely, which is why it's not used, because it can be also a bad trip, so to speak. But you're conscious, and the response, even if the person is unresponsive, the response of the brain suggests high complexity, high phi. This is just to tell you that this can now be done in rodent. These are our data using neuropixel recordings in a rat. And here you see the response, the evoked response, the local field potential, and here the units, every little dot is a unit firing across the depth of cortex, hippocampus, and thalamus. And you can see that in the cortex, when the animal is in deep non-REM sleep, there is an off period. So we can confirm that units stop firing for roughly 200 milliseconds after the initial response, when the animal, in this case, in non-REM sleep. For that matter, that's also true for sevoflurane, dexmedetomidine anesthesia, and it's back in REM sleep. So an index the perturbational complexity index that quantifies this complexity is indeed behaving just like in humans, high in wake and REM and low in the other condition. And the reason it's low is because you break causal interactions during the off period in non-REM sleep. By the way, this we also simulated quite some time ago. Now we have more recent simulations. Basically we understand reasonably well what's going on in the 3 layers of cortex, 3 main layers, supra, infra, and layer 4, and then in the thalamus. In sleep, you get this off period, this brief, everybody shuts off, that kill the causal interactions and therefore consciousness. This is just a summary that across hundreds of subjects now, you can see that if you measure this index of integrated information, a very crude index, it's always high. These are different subjects when subjects are awake, even neurological subjects with locked-in syndromes of cortical strokes, emergence from the minimally conscious state, and importantly, when they are conscious but unresponsive, like ketamine and dreaming. But it's always low when they are in an unconscious situation, non-REM sleep, midazolam, xenon, and propofol anesthesia. With very high sensitivity and specificity, there's really nothing sort of like that. So that was a prediction of IHC, and then it can be used, for instance, vegetative patients, to find out where behavioral responsiveness is not really a great guide, whether they may be there or not. If the values are 0, then presumably there is nobody there. The values are low, but like sleep or anesthesia, maybe there is a chance to wake up these people with deep brain stimulation or drugs. And when the values are similar to what we observe in ourselves when we are conscious, there are reasons to believe that these people are there, as we know from other paradigms, and to try to use brain-machine interface to communicate with them.
And so in one of the experiments in 2023, the scientists wanted to find out one simple thing. Can anesthetics affect microtubules directly, thus possibly providing evidence that there might be something about them in terms of consciousness? Here's actually a physical picture of microtubules inside a typical cell. And here's another picture of different cells connected together, and microtubules shown in green. And so for this particular experiment, the scientists took microtubules and they basically made them glow because a lot of them do display fluorescence. But then they decided to test something about this fluorescence. They added certain anesthetics into those microtubules and it surprisingly changed the way they glow. In other words, they actually discovered that a lot of fluorescence seems to have a substantial delay when microtubules are mixed with anesthetics such as, for example, xenon. In this case, the effect is actually really small. The actual delay was only about 20% or so, but it provided important evidence that there is a connection between anesthesia and microtubules. Or in other words, it actually provided important evidence for something that Hameroff proposed back in the 80s. But that doesn't obviously prove anything in regards to quantum mechanics. None of these effects so far are quantum in nature. And that's until we come to this recent paper that as always you can find in the description below. And I guess in some sense, if you watch this whole video, you can probably understand what this title says. Here they used a mega network of tryptophan, or basically once again microtubules, in order to provide first ever evidence for quantum effects. And the reasoning behind the study was somewhat unusual. Here the researchers once again realized that this is a kind of a crystalline structure. A crystal-like biological structure that makes microtubules a very attractive candidate for all sorts of quantum entanglement. And this idea has been previously explored in other papers, but never physically proven. And so here, by using microtubules that you can technically buy online from a lot of different biological companies, the researchers performed a super simple experiment. They used a more complex arrangement of these microtubules and basically made them fluoresce. By shining the UV light, these microtubules started to emit light back. But here, because of the arrangement and because of the structure, they actually started producing super radiance, very likely caused by the collective interaction inside these arrangements, which results in the production of light as a kind of a high-intensity pulse, different from what's usually expected in classical physics. But this is only something that happens when these molecules are arranged in symmetrical networks, kind of similar to what we usually find in various cells. If you just take a simple tryptophan molecule, or just a few of them, without a specific arrangement, they don't do any of this. And so this unusual quantum effect that produces stronger fluorescence has been now physically proven to exist inside microtubule structures. And by demonstrating that microtubules can indeed produce quantum effects, it creates a kind of an implication for a lot of studies of consciousness. Now, it doesn't actually prove that consciousness is quantum. What it does prove, though, is that it's not impossible. Here we now have physical proof that, first of all, microtubule arrangement can indeed produce quantum effects, and from that previous study, these quantum effects, or really any effects inside these microtubules, can also be affected by a lot of anesthetics, which by itself is a huge discovery for fields like quantum biology. But the main point is really to discover all of the quantum effects in various biological systems. And so if a lot of this is confirmed in future studies, and if many of these studies do discover that maybe consciousness is actually caused by microtubules, and maybe it is quantum in nature, this of course has a huge implication for a lot of fields, and more practically for medical fields. So here, one example that someone mentioned in one of the studies is things like Alzheimer's. There's actually evidence that Alzheimer's, which usually leads to a major breakdown of conscious activity, is very often caused by some kind of a protein buildup and, surprisingly, dissolution of microtubules inside neurons. And not just Alzheimer's, a lot of different types of dementia seem to be connected to microtubules as well.
One last thing I want to say in terms of definitions with this painting by Rousseau is that the greatest experiment of all neuroscience in my mind is the one we do every night when we fall asleep, and first we lose consciousness, and then at some point we dream. And when we dream, we have proof, undeniable proof, that the brain alone, the brain by itself, disconnected from the outside world, both in the input side and on the output side, is able to generate an entire universe of consciousness. In fact, it makes up the world all by itself every night. That is perhaps something to keep in mind. Consciousness is there whether the world is there or not.
There was a renovation happening in the apartment across the way from ours, and I was invited in my dream world. There was a real renovation happening, and they took me around, and it was crazy in there. There were stages and performers and circus, all this crazy stuff. But what really caught my attention was the height of the ceiling, because I knew that the ceiling couldn't be that high. So I said to the contractor, "How'd you get the ceiling so high?" He said, "Well, the outside of the building has a different shape in this part of the building." And in the dream, I said to myself, "That's not true. I know what this building looks like. This must be a dream." And I said to myself in the dream, I'm going to wake myself up and prove that this is a dream. And I shook myself in the dream, and I shook myself in real life, and I woke up. And so I'd never had that experience before. It was kind of a wild moment for me. But I gather that this is something now which science really can confirm, that there is this thing called lucid dreaming, where you can be in a dream and know that you're in the dream. So Ken, you've actually done some work on this, really establishing scientifically that lucid dreaming is a real thing. Can you tell us about that?
Yeah, I think it's been established that it was real for quite a while, but we had some additional questions. One of our questions was, can we do better with dream research? Because right now we find out about dreams only when you wake up. And you wake up, you're in a different stage. Your brain is in quite a different stage, and you forget a lot of your dreams, as we were discussing earlier. Probably you remember only a small fraction of your dreams, and you may distort the parts you do remember or forget details. And so we thought, well, dream research would be better equipped to understand dreams if we could also look at the brain during a dream and find out what people are experiencing. But we wanted to be able to ask people what they're experiencing, and we thought,
while they're sleeping.
While they're sleeping,
yeah.
If we could not wait for them to wake up and tell us about their dream, but ask them during the dream questions about what they're dreaming, then we would be better equipped to continue our studies and try to understand dreams and how they relate to memory processing and creativity and so forth. So we set out to do that, and there are two challenges. One is to have someone in a sleep lab in the midst of a lucid dream, and the other was to show that you can actually communicate with them. Because lucid dreaming, as you mentioned, is a bit rare. Not everyone does it. Even people that do it don't necessarily have a dream every time they would come to the sleep lab. And so we needed to provoke lucid dreaming. And so we basically took the method I had been using in slow wave sleep, targeted memory reactivation, and to try to transfer that to REM sleep. And so instead of having people learn the locations of objects before sleep, we had them learn a strategy of how to think carefully about the present moment and carefully decide, am I awake right now or am I in the midst of a dream? So we trained them to do that for a few minutes before sleep, together with an important sound. So there was some sound that cued them to go into that state of mind of carefully checking. It might be a little violin, or the sound of a harp, some beeping noises, and we use some lights as well. So different sorts of sensory stimulation that we could then present again when we know they're in REM sleep. So they do the training with the sound, they get the sound again during REM sleep, and that often provokes people to have a lucid dream. And so our first part of the challenge was successful. We can maybe make even half of the people have a lucid dream when we present those sounds with that procedure, the targeted memory reactivation, or we call it targeted lucidity activation in this case. And so, but how do we know they're having a lucid dream? Well, we had to give them some instructions. And so it's been known that lucid dreamers can move their eyes in their dream body, and their actual eyes will move too. And we can put electrodes on their face and record those eye movements. And if you make an eye movement to the left and to the right, very far in the distance, left, right, we can record that activity from our electrophysiological measurements. And that, in rapid eye movement sleep, you see some eye movements, but you seldom see all the way to the left, right movement. So it's a very distinctive signal. We can be very confident when we see it that the dreamer is signaling to us, understand that they're in the midst of a dream. So we've established that they're having a lucid dream, and they've given us the signal. Now, what wasn't known before was whether people could receive information and communicate back. And so that's what we did in my lab and also several labs in Europe that we published together. We showed that, well, if we ask a question to a lucid dreamer, they can give us an answer back with eye movements or a few other modes of expressing themselves that are available to them, of course, because they can't talk. Their body is mostly paralyzed, so they're unable to just sort of give us an answer to the question. But with eye movement signals or some muscle twitches or what we're using now, sniffing signals, we can measure responses from people because, of course, your respiration is still working during sleep, and you can control that, and you can sniff, and we can put a cannula near the nose to measure that sniff response.
What sort of questions?
So we wanted to ask questions where we knew what the correct answer was, not something about their dream, but something where we could verify it was the correct answer. So we settled on math problems, little math problems. There would be addition or subtraction, and the answer might be 1, 2, 3, or 4, and they would be told, move your eyes left to right the number of times for the answer to the question, and therefore they could answer the question. And so we've repeated this with other subjects a number of times. It doesn't work every time, but it's been repeated enough in our lab and other labs for us to know that we are successfully communicating, that people can hear a question, they can think about it, they can, understand it correctly, do a mental computation, little addition or subtraction, and decide what the answer is, and then produce the answer with their eye movement signals so that we can confirm that we've communicated correctly. And now we're moving ahead to ask more interesting questions besides math problems to find out, well, what are they dreaming at the moment? What is their experience of the moment? And then asking, and what's the brain activity at the same time? And how do we relate those two so we can understand more and more about dreaming?
And what do the participants say after they wake up? Do they remember being asked a question, and do they remember the process by which they came to the answer in the dream state?
Yes, interestingly, not always do they remember, but many times people remember the question. And so they would wake up, they would tell us what they were dreaming. There are other people that heard the question coming from some aspect of the dream. So one person was in a car and it sounded like the questions were coming from the car radio. Another dreamer thought it was coming from the ceiling, just like someone talking to them out of nowhere. And of course, some people don't respond at all, so they may not have a lucid dream, or they may not have the capacity for the information to come from the outside into their dream.
So I'll finish the first part by just pointing out, which will be important for later, one key implication of IIT with respect to difficult questions about presence of consciousness in other species very different from us, in cortical organoids, or is there such a thing as collective consciousness? The only one I want to point out is computer consciousness. Okay, now with artificial intelligence, especially with artificial general intelligence, we are getting to the stage in which computers are becoming more and more functionally equivalent to us. They can do most of the things we do, sometimes even better. They're not there yet, but the key point that follows from IT, it's an implication very much like the one about free will I will discuss next, is that if IT is right, a computer, a super powerful computer that might even completely simulate in detail the activity of the neurons in my brain by having a precise notion of the connectivity and their properties, will not be conscious at all. This is done with a very, very simple system, A, B, C, D, which we unfold. We see its cause-effect powers unfolded here, a cause-effect structure with some decent phi value. And here a much larger physical system of 55 gates as opposed to 4, which is actually able to simulate in detail, indefinitely, the behavior of this system. So this is a computer that simulates this little system, okay? If you consider these two in physical terms as two substrates and you unfold them, you unfold the computer, and far from getting a large cause-effect structure, you get a bunch of mini entities indicated here corresponding to their memory registers and the clock. And the computer as a whole is nothing at all. Its phi is 0. In this case, because it's feed-forward, but it doesn't even matter. It's just the architecture has a bottleneck, is very bad for integrating information. So it does all the things this other system does, but it has no intrinsic existence, no consciousness as such. Being is not doing. And so when we get to our own subset of consciousness, let's say primarily in posterior cortical areas, which unfolded would be a giant cause-effect structure, as I indicated to you, at least when we are awake or dreaming, a large computer, because it's a computer, that would simulate it, might be able to do all the things we do, but there would be nothing there. There would be nobody home, no consciousness except for this minimal set of micro entities corresponding to the memory registers and the clock, which in the end, leads to the final slide. That is that there is a double dissociation between consciousness and intelligence. Usually we tend to consider them together because there are reasons, I won't discuss them now. We actually published a paper on this, while with a selective pressure, you might actually get that, generally speaking, consciousness and intelligence sort of may grow together. But in general, you could have a supercomputer that is very intelligent and has no consciousness whatsoever, and an organoid in the proper condition that may even be conscious, let's say, of space, but be totally stupid because it cannot do anything. It doesn't even have inputs and outputs. I will then move to the implications for free will. And I'll call it, broadly speaking, the intrinsic existence view, because it will be compared briefly to what I think is the more common way to think about everything, including free will, which is the extrinsic existence view. So then I'll remind you, we start from the experience. We finally come up with the idea that to account for the experience in physical terms, we need to fully unfold the substrate and reveal all its causal powers. And we get this global maximum of intrinsic, structure, specific, irreducible cause-effect power as dictated by the postulates. The quality is the form, that is all the distinction relations, and the quantity is how irreducible it is. I also, discuss, for instance, space. The idea is that any content of an experience, like the extendedness of the visual field, the feeling of time flowing, an object like my body I might be seeing, and the colors, etc., everything that exists as a content of an experience exists physically according to IT. Everything is physical in this very precise way of understanding physics as operational cause-effect power. And to be more specific, it is a substructure within the cause-effect structure. So if you're having this experience right now when you wake up from your dreamless nap, then it's a giant cause-effect structure indicated here in gray, only partially. And within that, distinct contents, like for instance, the feeling of extendedness, is a substructure. And objects will be other substructures and so on and so forth. So here, the key message I want to get across then is that if what exists immediately and indubitably, which I say truly for simplicity, is experience, and if experience has 5 essential properties, the action of IT, and if a physical substrate is an operational basis, note, not a supervenience basis, is an operational basis, we can play around with it, observe and manipulate. That's all we can do physically, okay? Always as conscious being, by the way, conscious is always first, is a set of units in a state, like neurons in the brain. And we fully unfold its causal powers. People normally don't do that. They think about the substrate and then just see what it does. But we want to actually fully unfold its causal powers, which is what IT allows you to do, in principle, at least for simple systems. And then the key thing to realize is that what truly exists, what is identical to the experience, is the cause-effect structure and not the substrate as such. It's a key message to try and get across. We are used to the brain, the neurons, what we observe, manipulate is what exists, and then it carries stuff on top of it. We'll get to that in a moment. But IIT tells you, what exists is the substrate unfolded, the cause-effect structure, not the substrate as such. And so here, I want to give you sort of a visual sense of what that means then. For any substrate, say the brain, okay, IIT requires that you in principle would unfold it completely. And it will yield, once you do this full unfolding, when you see all its causal powers, one, for instance, giant intrinsic entity, one giant cause-effect structure indicated here, sort of like a giant cruise ship, if you wish, surrounded by a huge number of little sailing boats, as it were, which are these mini entities like the cerebellum and probably parts of prefrontal cortex and all kind of other things. And they are disjoint. None of these entities overlap. What there truly is, if the IT picture is correct, is a bunch of intrinsic entities, some very large, like our own consciousness, and some very small, like stuff that sort of exists in cerebellum, prefrontal cortex, spinal cord, and everywhere else, so to speak, interacting among themselves. That's just exclusion in action, if you wish. It's called horizontal exclusion because you cannot have overlap between these intrinsic entities. And then there is a vertical exclusion, which I didn't really discuss at length. I only mentioned that we have several papers on that, which says that these entities exist based on units that have a particular grain, a grain like neurons versus microcolumns, mini columns, you name it, or anything smaller than that, proteins, atoms, elementary particles. And here it's indicated, for instance, the grain could be neurons. I think this is an open question, one we're actively working on. Is it neurons that have maximal power, or is it anything coarser or finer? Is it over 20 milliseconds or 2 milliseconds or microseconds? Probably not. Or seconds, tens of seconds. There is going to be one grain and a particular set of states at which intrinsic existence phi is maximum. So there is horizontal and vertical exclusion. What truly exists is a bunch, in physical terms, a bunch of intrinsic entities, each of which with substructure, with their particular contents, at a particular grain, period, okay? Now, what we typically do, which is absolutely fine empirically, is we look at it extrinsically. We can analyze, study physically anything we want, any set, any superset, any subset, at any grain we want. We can study the body, we can study the brain, we can study parts of the brain like posterior cortex, we can study the fusiform phase area within it. Anything we want, we can study operationally, physically, and find cause-effect power, of course. And we can do this at the level of neurons, at the level of channels, proteins, atoms, if you wish, or mini columns. Anything is fair as long as you can show physical existence. But that's okay for explaining things, for accounting for things, and that's the domain, of course, of the spatial sciences. But it's not okay ontologically. The principle that matters here, I will not show the others from IIT, follows from the maximum existence principle. It can be called the no free existence principle. Cause-effect power cannot be multiplied over the same substrate. So in other words, once we unfold all the causal powers of, say, posterior cortex, you cannot physically have those powers as well as the powers of the supersets, like the cortex, the brain, the body, all on top of it, okay? Or subsets, posterior cortex, but also the causal powers of fusiform phase area and also the ones of particular subregions of it. There's only a set of disjoint entities. That's the horizontal exclusion. And you cannot physically have coexist the causal powers of neurons, if they are the fundamental unit, as well as that of their organelles, their proteins, their atoms, as well as that of the mini columns, voxels, and regions to which they contribute. So there is anything you can do is fair, but in the end, what truly exists are only distinct, disjoint intrinsic entities at a particular grain. That's the intrinsic existence view versus the extrinsic existence view. And now here we come to the ontology, so to speak, that's relevant also for free will. So this whole story says that when I am conscious or whatever, I exist intrinsically as a cause-effect structure in physical terms, not as a substrate. And of course, only I exist, not my subsets, supersets, or parasets, and at the grain at which I exist, not at finer and coarser grains. Now, anything that's the content of my experience also truly exists, but it exists physically as a substructure within a cause-effect structure. That's true for space, time, objects, and colors that I might experience. It's true for thoughts and feelings. It's true for alternative reasons, decisions, will, intentions, agency, self-values, you name it. Problems, solutions, question answers, anything you might think of. So what I indicate here are different experiences, so to speak, that you might have at different moments, which is what exists, and within it, different contents, okay, that have their particular shape. And perhaps the most important message here for this part about the freedom as opposed to the will, if we go back to our sort of paradigmatic free will scenario, a very, very crucial step in my mind is the existence of alternative courses of action. The moment in a typical deliberative process, I think to myself consciously, I could do this or that, which is a typical thing, where that could also be not this, it doesn't matter. What is that? Well, IIT tells you that what there is an experience which truly exists as a cause-effect structure, and within it, indicated here by these sort of two silly horns in yellow and in green, are two substructures related among themselves that only exist as intrinsic content of experience. They are substructured, they are physical, and they are the only alternatives that are worth their name. The alternatives that exist in my mind. That is where freedom resides. And it does not reside in alternative trajectories of a substrate unrolling over time, as is normally thought. They don't exist. The substrate as such does not exist. At any moment, all that exists is this. That's what truly exists. Consciousness as a physical cause-effect structure. And these hypothetical trajectories that we can conceive, whether we introduce or not indeterminism, are neither necessary for true freedom, because they don't exist, nor are they sufficient, because if there is some alternative at the micro level because of indeterminism, it merely introduces essentially chance and not really any freedom. So you can sort of see here, remember this, it's a vertical alternative between two possible courses of action in your mind, not a horizontal alternative as what the substrate might be doing. There is no such thing as the substrate, but only the substrate unfolded. So then the same holds true for reasons. When I consult my reasons consciously, basically those exist again as substructures within a cause-effect structure, as contents of my experience, and they exist physically. So that's what exists, and that is what is instrumental in leading to a decision. A decision is also a substructure in my experience, and the decision is, of course, going to be followed by an action, typically, and usually also by another experience, which is, of course, the feeling of agency, typically associated with control. So this, in short, is a very, very quick and sketch of how the ontology of IIT applies to the situation of free will. What truly exists are experiences, and these are cause-effect structures, and within them, all kinds of contents, space, faces, colors, you name it, but also alternative courses of action, reasons, and decisions. And they truly exist and only exist as forms in the mind. Now, this leads me, I told you need an ontology, but you also need an account of causation. Otherwise, you get sort of the freedom, but you don't get the will. Okay. For that, you need to answer the question of what caused what. And this has been the focus of our efforts for quite some time now, to try to get a proper, mathematically coherent way of measuring what causes what. It's called causal structure analysis. In essence, I'll go very quickly here too, is based on the same postulates of IIT, because after all, cause-effect power is about existence, and what causes what is tightly related to it. Instead of existence here, you have realization. To measure actual causation, what caused what, you need two occurrences. An occurrence at time t-1, say a system in state A, B, C, D, some on, some off, and then another occurrence that actually happens at time t0, for instance, this one, in which you see D turns off, for instance. And then you can ask, in this transition between two occurrences, which actually happened, okay, what caused what? And in IIT, just like intrinsicality required that the cause-effect power be inside, for actual causation, you must look in both directions, which is typically not done. You can ask what are the causes from the occurrence at t0, the cause at t-1, and you can ask what are the effects of t-1 to t0, and they are not typically the same. So you need to analyze both directions. And you do the analysis compositionally. That is, you should ask not just for the cause of A, B, C, D, or just of A, which would be like the holistic or reductionist approach. You have to ask for the causes of C, of D, of CD, and so on and so forth, and their relations. You have to ask precisely what caused what and get a quantity, a measure of the efficacy of causation. And it's only causal if the cause is irreducible. If A is caused by something and B is caused by something, and they are caused independently, there is no joint cause. And you can measure this explicitly again with the tools of IAT. The quantity in this case is called alpha and not phi, and it's measured quite precisely. So we can tell if there is an irreducible cause, and that's the only cause that matters. And finally, we can also apply exclusion and ask, well, does the cause include everything, including all the cosmic rays that may be happening now that sort of were also involved in causing an accident? Or, you know, for a neuron, it fired because of the input through all its 1,000 synapses as opposed to the 3 that fire very strongly. There is a principal way to answer that. You find what causes the most, and that is what, in the end, the causal structure analysis gives you, a principal way to measure what caused what. Again, I refer you to the fundamental paper, which is this one, which is providing all the fundamental examples for this. It allows you to take, for instance, a little agent, this is called an animat, with sensors, effectors, and a little brain, and explicitly work out all the causes and their strength, all the effects and their strength, alpha, and provide, therefore, a causal account of a transition between two occurrences. This causal analysis is moving on. It's not finished yet, but we have made at least some progress in attacking in a principled way questions like, are there macro causes versus micro causes? And again, the IAT approach says that macro causes can exclude micro causes. That is, there is macro causation, depending how the system is built, that exclude micro causation. This is the opposite of, you know, Kim's notion of causal exclusion being micro-physical causation is what causes, the rest is carried along. No, you can show once you have an actual measure of causation that macro units can cause and not the micro units. The macro beats the micro, we call it. Importantly, for free will too, you can backtrack causes. I won't show the video here and everything else, but it's just basically the idea that you can ask meaningfully the question of, given an occurrence, we can backtrack in time when the distal cause actually was, and beyond which instead there was no distal cause, again using a criterion of maximality. So we can actually track what caused it and how far in the past. Okay, that's backtracking. More generally, you can use this analysis. I won't explain the figure on the left, the paper in press, but causal structure analysis connects sufficiency accounts of causation in philosophy to counterfactual and probabilistic accounts, that is interventional accounts, the counterfactual ones, and extends naturally to any probabilistic or non-binary scenario. It can account, as we show in that paper, for many, many philosophical puzzles of causation. The moment you put them in these precise mechanistic terms, you can actually get a meaningful answer to most of the classic examples. To me, very importantly, it demonstrates the incoherence of causal reductionism, or the idea that's sort of permeating sort of much of our thinking in general, that what really causes micro events at the micro level. No, actually the exclusion goes the other way. There is high order causation, there is macro causation. And finally, it provides a coherent account of the difference between causation and prediction. I won't go into that now, but it'll come back when we get now to the final point about free will. And that is the sentence that sort of captures the most important implication that sums together the ontology and the causal structure analysis part, that only what exists can cause, where of course I mean truly exist as an intrinsic entity. Only what truly exists can truly cause. That's the final real message of the IAT approach to consciousness and its implication for free will. Remember this. So at any moment, there is an experience which has contents, which could be alternatives, reasons, and then finally a decision. Now, a decision is a substructure within a cause-effect structure, is a physical thing. Now we can ask, in principle, if we have the right tools, what caused my decision? And here it is enlarged. It will typically be an alpha structure, a causal account, the way I sort of briefly described to you, which will connect some substructure within an intrinsic entity here, this cause-effect structure, which is my decision now, to its causes in a previous, so to speak, experience or state of mind. And particularly, it will connect it also in part to reasons, which are also physical. They are substructures. So you can actually measure what caused what, my decision, by which reasons within my experience. All of this truly exists, and it has an actual strength, alpha, of causation. You can also measure in the effect direction, what did my decision cause? Language is unfortunately very confusing about this. What are the effects of my decision on, for instance, the action that I might perform? And again, only what truly exists can cause. This truly exists, this substructure and my decision truly exist, they can actually cause. We can, in principle, measure that and then attribute, the true cause and the true effect. I want to remind you now, just to give a very quick snapshot of what difference this makes. Before I showed you the false from IIT, that a computer that were able to simulate my brain in detail will do everything I do, but it will be nothing whatsoever. It will be not conscious, it will not be an intrinsic entity. And here I'm showing you, so to speak, a computer that is simulating my decision and the previous state of my brain when I was sort of going through my reasons and the subsequent action, if you wish. So in principle, a computer could do all of that, but it doesn't exist as a whole. There are just micro entities only. At any time point does it exist, and therefore it doesn't truly cause. All the true causes here are just trivial, say, transistor to transistor causes, a bunch of them, and not entity to entity causes or substructure to substructure causes. So it doesn't exist. It exists for us, but not for itself. It doesn't exist intrinsically, truly, and it doesn't cause truly. It's as if it existed from the outside. It looks like one of us, and it's as if it had free will and caused. But none of that is true once you have your ontology and causation correct. So I want to show you this slide, which of course is a parody of what probably many people might think. It doesn't really necessarily capture anybody's specific notions, I'm sure not in this group, but there is this overwhelming sense that we carry with us that after all, the physical substrate, like the brain, the neurons, and ultimately the elementary particles, exist down there as the supervenience basis or the grounding for everything else. And then there is microphysical causation such that we go from here to here to here and then to an action. And then everything else, well, obviously, except for, strict atomists, we do think it's important. We don't think that it's not there, we shouldn't talk about it, but it's due to essentially vertical determination, if you wish, a kind of supervenience in which you can talk about anything you want, including here functional state one that might correspond to I could do this or that, which of course is vertically determined. And it's carried along for the ride. That's the best way to put it. This exists. These may exist too in some sense. Maybe they're not physical, but we cannot do without them for explaining who we are, what we do, and what causes what. But really, in the end, the bottom is carrying the day, okay? And so we go from here to here to here, and this continues to exist in the usual way of seeing things. And all the supervening stuff is there. We cannot help talking about it because, of course, there's multiple realization and many other reasons. We cannot do anything but giving causal explanation at this level. It doesn't make sense otherwise. But truly, down deep, so to speak, is the microphysical substrate and the microphysical causation that carries the day, as opposed to the intrinsic existence view that the substrate doesn't exist. Once you unfold it, what exists is just the cause-effect structure, the conscious entity that exists and causes. So I will now finish. I know it's been a lot. This will be easier in a way. I want to just make one point about the role of indeterminism. I'm not going to go at all into compatibilism versus incompatibilism, but I will just say, because it's important, that IIT actually requires indeterminism from first principles. So to exist, you must have, cause-effect power, that is intrinsic, structure-specific, unitary, and definite. We saw that, and then you exist as a cause-effect structure. But to have cause-effect power, intrinsically, you actually, even as an elementary unit, whatever that might be, in this case, obviously not a neuron, but an atom or an elementary particle, you must have a way to take and make a difference to yourself intrinsically. You must make a difference, otherwise there is no causal power. And you must have at least two states available to you, always present, available intrinsically. Otherwise, again, you cannot take a difference. So in essence, there is a trade-off between determinism and indeterminism, which is mandated by the requirements for existing in IIT. And it's interesting, it actually gets a mathematical value for exactly what is the right value of indeterminism to maximize existence. So there has to be indeterminism, by the way, which means, of course, that the future is open-ended, also according to IIT, and not just to sort of modern physics, and the past is not predetermined. And my last point will be this. So what does this entail with respect to now the longer term story of historical determination, this feeling that we often have that no matter what, sort of we are determined by what happens to our genes, to our environment, to our life experiences, and so on and so forth, okay? And where does personal responsibility then come into this picture? So here I give, just again as an illustration, a view that some people certainly hold, which is obviously discouraging, in which from the Big Bang on, so to speak, it's just one damn thing after another. You know, this determines this, which determines that, which determines that, and maybe some indeterminism here and there, but essentially, inevitably, what follows what was before in a way that could be predicted, for instance, to some extent. In any case, it's a long chain of determinations. And therefore, in this view, in some sense, nothing is ever truly my responsibility, but is determined by previous occurrences and, to some extent, chance. Now, I'm sure you have discussed this at length, and there are ways to sort of think about this, but for sure, it's a lingering thought. What does IIT have to say? It has to say that the story is radically different. The intrinsic existence view says that my decisions are truly my responsibility, and increasingly so with self-forming actions and rationality. And just I illustrate this by saying that what truly exists, again, according to IIT, is not the substrate. At first, it's just this, what I call dust, possibly many, many micro entities with minimal values of phi's that count for nothing, okay? That's the universe at the beginning. Then consciousness, this is the first big discontinuity, emergence at a high level. And here I mean emergence just in the temporal sense. Suddenly there is some big entity, like this primitive fish or primitive mammal, where there is true existence. And the baby, of course, would be possibly even more true existence. So there is consciousness, something exists rather than nothing, and exists a lot as measured by phi. The second big discontinuity is when at a certain age, it's typically a gradual process, you actually have contents within consciousness, substructures in a cause-effect structure, corresponding to alternatives, reasons, and therefore, willed decisions. Then, for the first time, you truly have free will. This free will is there, so you are, by the account I gave you, acting on your own free will. Now or later, it's your decision, but it's still largely devoid of responsibility. The free will acts on something that was largely determined by what happened before, so to speak. It's then when you begin to have self-forming actions, I don't mean strictly in the sense of Cain, but more, going back to Aristotle, if you wish, in which you decide that you want to learn medicine because you want to help the world and help other people, okay? You do that. Of course, you're going to change all kinds of things, including things in your brain. You're going to change the substrate and therefore change what exists. And the more this accrues, the more of your own free will, your responsibility increases because you are a consequence, an effect of your free will. And when you're an adult doctor, for instance, then not only do you have high phi and a high level of consciousness and all the reasons and the beliefs and the understanding that you have, with it comes high responsibility because now you have been responsible for who you are. And finally, to me, the last discontinuity is the one in which when you also get hold of rationality as a method, the method to examine your reasons and beliefs in an impartial manner, of course, aided by a society and by science, as opposed to as what was determined by your past, you really become fully and truly free, and you really become truly and fully responsible.
The big news from the Hubble Space Telescope this week was that it had spotted the most distant star ever found at 12.9 billion light years away and nicknamed Earendel. Now, you'll have probably seen this in the news already, but now it's time to dive into all of the nitty-gritty astrophysics details, like how did they find this thing? How do they know how far away it is? And how do they even know that it's a star? And is there a chance that it could be something else entirely? So let's dive into this. This study has been led by Welch, Coe and collaborators who have been targeting big clusters of galaxies with the Hubble Space Telescope since about 2016 in the hope of finding things like this, known as arcs. These are galaxies in the background, behind the ones in the big galaxy cluster in the foreground that you can see. And the cluster is just one big lump of matter, right? You know, like hot hydrogen gas and dark matter, just all pockmarked then with galaxies of stars, kind of like a chocolate chip cookie. And all of this matter curves space, right? This is how Einstein described gravity in his theory of general relativity, which means that light from those background galaxies travels across that curved space and gets bent into these arcs. This is what's known as gravitational lensing, because that cluster of galaxies in the foreground acts like a lens to change the path of light, just like the bottom of a stemmed wine glass does when it passes in front of a candle in the background. And just like a lens, that cluster of galaxies can also magnify things in the distance as well, taking those, very faint distant galaxies that we wouldn't usually be able to spot and making them much brighter so that we can study them. And because light has this finite speed limit that it can't go faster than, light takes time to travel to us. So we're seeing those very distant galaxies as they were billions of years ago when the universe was much younger. So by studying them, what we can do is compare what did the universe look like then compared to what it looks like now when we look at nearby galaxies. And can we piece together what's happened in terms of how the whole universe has evolved to give us what we see today. So this is what Welch and Coe and collaborators were looking for at first with what's known as the RELIX survey. And in that data, they spotted the longest arc they've ever seen at a distance of 12.9 billion light years away. They know that this arc is that far away because of the different wavelengths of light that they can and can't detect from it. So when the light from this galaxy has been traveling through the universe to us, the universe has been expanding. So the light is stretched to longer wavelengths. It is redshifted. But on its way, it also passes through random clouds and clumps of hydrogen gas that just permeate the universe. And the hydrogen gas actually steals away a very specific color or wavelength of light as it passes through. As the light travels further through the universe, more light gets redshifted to become that specific wavelength that hydrogen likes to absorb and steal away. And so what happens is you start to lose all the light beyond a certain wavelength. If you take a spectrum of the light from the galaxy where you split the light into all of its different component wavelengths and get a trace of how much of each wavelength you detect, then it's really easy to spot, right? Like in the example I'm showing here. But the giant arc they detected here was actually too faint for Hubble spectrograph to even be able to detect. So instead what you can do is you can take images through filters that only let in like certain regions, certain wavelengths or colors of light. And from where you do and don't detect light anymore, you can pinpoint, well, how much has the light been redshifted and therefore how long the light has been traveling for to know how far away the object was when the light left it. And in the case of this arc that they spotted, that was when the universe was less than 1 billion years old, practically a baby in comparison to the 13.8 billion years old that we think it is now. So what they did after spotting this arc was they actually applied to observe it again with the Hubble Space Telescope, but this time for longer in the hope of collecting more light to see more detail. They got that image back in 2019, 3.5 years after the image that the arc was originally spotted in. Now, along any arc, you also get clumps as well, which could either be light from the center of a galaxy where it's brightest or from a star cluster in that galaxy that's really quite bright as well. And usually those are seen in multiple places along the arc due to how the lensing works, like the things highlighted in cyan here. This is a star cluster seen 3 times. But then there's also this bright point which is only seen once in both the images taken in 2016 and in 2019, which the authors of this study identified as a single star in this galaxy that's 12.9 billion light years away. We'll get to how they identified it as a single star in a minute, but I just wanted to talk about how it was even possible for them to detect a single star at that kind of distance. Because when you look up to the night sky, every single star that you see is from our own galaxy, the Milky Way, a few tens of thousands of light years away. The Hubble Space Telescope has just enough resolving power to make out individual stars in the Andromeda galaxy, which is our largest, nearest neighbor galaxy. But anything further than that, and the light from the stars have just merged to give us just this glow of a galaxy. It's only when they die and go supernova do we have a hope of picking out individual stars, but even that has its limits in terms of distance, out to about 10-ish billion light years away. That isn't what we've got here. This isn't a ridiculously bright supernova. What we've got is a star that's just in the right place at the right time. The star just happens to be perfectly aligned with the clump of matter that's doing the lensing, so much so that it gets magnified to over 1,000 times brighter than it normally is so that we can spot it. The best analogy that I've heard for this is that the matter in the cluster is acting kind of like the ripples on the surface of a swimming pool. You know, it transforms the equal amounts of sunlight that's incident on the surface of the pool into these patterns on the bottom of the pool, which are analogous to the arcs. You know, in these patterns, you can see there's always that odd bit that is that much brighter than the rest. This is what's happened to this star, WHL 0137-LS, but nicknamed by the authors as a Earendel, from the Old English word meaning morning star or dawn star. And